On November 2nd, 2025, something appeared in the space between Earth and the most mysterious interstellar visitor ever recorded, and it arrived with no warning, no tail, and no explanation that fits what we understand about how the universe works. What you're about to discover could rewrite humanity's understanding of whether we're truly alone, whether intelligence beyond Earth not only exists, but is here now studying us from the dark between worlds. 10 observatories across the planet confirmed it independently. The object sits positioned with mathematical precision between Comet 3I Atlas and our world, discovered by the same astronomer who found the second interstellar visitor in history, and NASA's own data shows something is accelerating in ways gravity cannot explain. But here's what keeps astronomers awake at night. If this is natural, why does it defy every law of cometary physics? And if it's not natural, what is it doing here? Tonight, we journey into one of the most profound mysteries modern astronomy has ever encountered. Over the next 2 hours, we'll examine 10 scientific anomalies that challenge everything we thought we knew about interstellar visitors. We'll explore what ancient civilizations might have witnessed in their own skies and ask the question that defines our moment in cosmic history: are we being watched? The universe keeps its secrets well, but every so often something crosses the boundary between the known and the unknown. Something that makes us reconsider not just what we understand, but what we're capable of understanding. This is that moment. This is that something. Welcome to the night when the sky changed. In the hours between November 1st and 2nd, in a modest observatory in Crimea, Gennady Borisov sat at his telescope as he had countless nights before. The air was cold, the sky was clear, and somewhere in the field of view of his custom-built half-meter reflector, a point of light existed that had not been there the night before. This is how the extraordinary often arrives quietly, without fanfare, noticed only by those patient enough to watch the same patch of sky night after night, looking for the one thing that changes. Borisov is not a household name, but in astronomical circles, he carries a particular distinction. In 2019, he discovered 2I Borisov, the second interstellar object ever confirmed by humanity. The first to clearly display cometary activity, an icy visitor from beyond our solar system that arrived, passed through, and departed forever. His name became attached to it, not because of institutional affiliation or professional credentials, but because he saw what others missed. And now, 6 years later, in that same Crimean night, he found something else. The object appeared as a fuzzy point magnitude 12. To put that in perspective, your naked eye can see stars down to about magnitude 6. Each number represents a brightness decrease of about 2.5 times. Magnitude 12 requires serious equipment, a good telescope, dark skies, and patience. It's the threshold where the universe begins to reveal secrets invisible to casual observation. Borisov noted the position, took multiple images, calculated the motion. Within hours, he reported the discovery through proper channels, the Minor Planet Center, the clearinghouse for such observations. The designation came swiftly: C 2025 V1 Borisov. The C indicates a comet. The year and letter code place it in time. And the name, well, that belongs to the finder. By November 5th, 10 separate observatories had confirmed it. Not amateurs with backyard telescopes, professional facilities with decades of experience observing comets. The Arnav Observatory in Spain, the Virtual Telescope Project in Italy, ground stations across hemispheres and time zones, all pointing their instruments at the same coordinates, all seeing the same thing: a nucleus, compact, defined approximately 1.5 arcseconds across, a faint coma surrounding it, and a stubby tail barely there, stretching 7 arcseconds toward position angles between 250 and 260 degrees. Here's what made it strange from the beginning: that tail should have been larger. Much larger. Comets are defined by their tails. Ancient peoples called them hairy stars because of the luminous streams that trail behind them. The Chinese recorded them meticulously in dynastic chronicles. The Babylonians saw them as omens. Medieval Europeans feared them as harbingers of plague and war. Every culture that watched the sky knew comets by their tails, those sweeping banners that point away from the sun like cosmic windsocks. V1 Borisov had almost nothing. A stub, a whisper of what should have been there. But there was something else. Something that took days to fully register once astronomers plotted its orbit and calculated its trajectory. It sat directly between 3I Atlas and Earth. Not approximately, not in the general vicinity. Directly in the geometric line connecting the most anomalous interstellar visitor in recorded history with our planet. In the vast, three-dimensional chessboard of the solar system where objects move, on planes tilted at different angles, where orbits intersect and miss each other by millions of kilometers, where the probability of any two objects aligning from Earth's perspective is vanishingly small, this new object appeared exactly where it would need to be, to sit between us and something already being called unprecedented. The timing made it stranger still. Everyone had been watching 3I Atlas. Since its discovery in July, it had dominated every telescope schedule, every observation window, every astronomical press release. An interstellar comet, only the third visitor from beyond our system ever detected, exhibiting behaviors that didn't fit comfortable models. While the world fixated on 3I Atlas, while instruments tracked its approach to the sun, while debates raged about what it was and what it meant, something else slipped into position, unnoticed, unannounced, arriving in the space between. And nobody saw it coming until Gennady Borisov, on a cold November night, looked in the exact right place at the exact right time. Ancient astronomers would have called this an omen. They tracked the heavens with naked eyes and remarkable precision, noting everything that moved or changed. The Mayans built entire calendars around celestial cycles. The Egyptians aligned pyramids with stellar precision. The Polynesians navigated thousands of miles of open ocean by reading the stars. They knew something we sometimes forget in our age of data and instruments: the sky tells stories. And sometimes those stories begin with a single point of light appearing where nothing existed before. V1 Borisov made its closest approach to Earth on November 11th, just 9 days after discovery. It passed within 103 million kilometers, roughly 0.69 astronomical units, where 1 AU represents the Earth-Sun distance. Not close by terrestrial standards, but close enough to matter. Close enough that if this object had any interest in studying us and positioning itself for observation, this would be exactly the geometry to choose. The minor planet center's circular was clinical technical, stripped of speculation. It reported the observations, the confirming stations, the calculated orbital elements. It noted the cometary nature based on the fuzzy appearance and faint tail. It assigned the designation and moved on to other business. But in observatories around the world, in university offices and research centers, in the quiet hours, when scientists stare at data and try to make sense of patterns, questions were forming. Why here? Why now, and why in a solar system empty enough that interstellar visitors should be rare beyond measure, did two of them suddenly occupy the same region of space, aligned with Earth in a configuration that probability alone could barely explain? The night sky had changed, not dramatically, not with fire or spectacle, but fundamentally, because once you see a pattern where randomness should reign, once you notice an alignment, where chaos should dominate, you cannot unsee it. You can only ask, what does it mean? And that question, that simple human impulse to find meaning in the movement of lights above, connects us to every ancestor who ever looked up and wondered. Every ancient priest tracking Venus, every navigator reading the Southern Cross, every philosopher contemplating the plurality of worlds. The discovery of V1 Borisov wasn't just an astronomical event. It was a moment when the universe whispered something just loud enough for those who were listening to hear. What it whispered, we're still trying to understand. To understand V1 Borisov, we must first understand what it appeared beside. We must trace the path of 3I Atlas from its origins in the dark, between stars, to this moment in our solar system. Because this object, this visitor from elsewhere, carries with it questions that reach to the foundation of what we think we know about the cosmos. 3I Atlas was discovered on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System. ATLAS for short, an automated survey telescope in Hawaii scanning the sky every clear night looking for objects that move against the fixed background of stars. The initial observations showed something unusual. The trajectory was hyperbolic, unbound from the sun's gravity. That alone marked it as special. Most comets in our solar system follow elliptical orbits, returning periodically. They're gravitationally trapped, destined to loop around the sun for millions of years, until collision or ejection alters their fate. Hyperbolic orbits are different. They're one-way tickets. Objects arrive from the vast interstellar darkness, swing past the sun once and depart forever. They're visitors, not residents. Only 3 such objects have ever been confirmed. Oumuamua in 2017, 2I Borisov in 2019, and now 3I Atlas. 3 visitors in 8 years. For all of human history before 2017, we detected 0, and now suddenly 3. That alone should give us pause. But 3I Atlas carried further strangeness from the start. Its orbit, when calculated with precision, revealed something unexpected. It travels almost exactly in the plane of the ecliptic, within 5 degrees. Imagine the solar system as a flat disk. The sun at the center, planets orbiting in roughly the same plane, like grooves on an ancient phonograph record. That plane is the ecliptic, defined by Earth's orbit, but representative of where most solar system mass concentrates. An object arriving from interstellar space has no reason to align with that plane. The galaxy is 3-dimensional. Stars move in all directions. An interstellar visitor, chosen randomly, should arrive from any angle with equal probability, up, down, sideways, diagonal through the ecliptic plane at steep inclinations. The probability of arriving aligned within 5 degrees of the ecliptic plane by chance, about 2 in 1,000. Not impossible, but unlikely enough to notice. 3I Atlas did more than align with the plane. It traveled retrograde backward relative to the planets, while Earth, Mars, Jupiter, and the rest orbit counterclockwise when viewed from above. The sun's north pole, 3I Atlas, moved clockwise through the same space, against traffic, so to speak. This combination ecliptic alignment with retrograde motion creates a specific observational opportunity. An object on such a trajectory passes through the inner solar system in a way that brings it near multiple planets. Not by accident, but by geometry. The architecture of the orbit itself guarantees certain encounters, and 3I Atlas's orbit delivered precisely such encounters. On October 3rd, it passed within 29 million kilometers of Mars, close enough that spacecraft orbiting the red planet, the Mars Reconnaissance Orbiter, the ExoMars Trace Gas Orbiter, China's Tianwen-1 could photograph it with resolution impossible from Earth. On October 29th, it reached perihelion, its closest point to the Sun, at a distance of 203 million kilometers, about 1.4 astronomical units, closer than Mars but farther than Earth. And on December 19th, approaching fast as I speak, it will make its closest pass by Earth, just 1.8 astronomical units. 168 million miles. A cosmic near miss, then outward toward Jupiter. On March 16, 2026, it will pass the gas giant at 54 million kilometers, close enough to feel the gravitational tug, perhaps using Jupiter's mass, to adjust its outbound trajectory in ways we can measure, and then gone. Departing the solar system forever, accelerating beyond the sun's influence, returning to the interstellar night from which it came. This trajectory, this precise sequence of planetary encounters, occurs with a probability estimated at 5 in 100,000. rare enough that witnessing it borders on extraordinary luck. Or something else. Ancient peoples understood celestial mechanics in ways that startle modern observers. They lacked equations, but they had time, generations of patient watching recording pattern recognition. The Babylonians predicted eclipses. The Mayans calculated Venus's cycle to within hours over centuries. The builders of Stonehenge aligned massive stones with summer solstice precision. They knew the sky was not chaotic. It was ordered, predictable. Patterns emerged from patient observation, and sometimes those patterns suggested purpose. When Halley's Comet appeared in 1066, visible during the Norman conquest of England, observers didn't see randomness, they saw meaning. The Bayeux Tapestry depicts it hanging over King Harold, presaging his defeat. Whether the meaning was real or imposed doesn't change the human instinct. Exceptional celestial events mark exceptional moments. Three-Eye Atlas is an exceptional event by any measure, not just because it's interstellar, but because of how it moves through our space. The ecliptic alignment, the multi-planet flyby sequence, the retrograde trajectory that makes it visible for extended periods from Earth's perspective. If you were designing a survey mission to study multiple planets in a single pass through an alien solar system, this is the orbit you would choose. It maximizes observational opportunities while minimizing fuel expenditure. It brings you close to multiple worlds, rocky inner planets and gas giants alike. It provides varied viewing angles and conditions. It is, in the language of mission planners, elegant. For a natural object randomly ejected from some distant stellar system billions of years ago, arriving here by chance alone, it seems almost too elegant. The size estimates add another layer of mystery. Based on brightness and estimated reflectivity, astronomers calculated that Three-Eye Atlas measures somewhere between 5 and 20 kilometers across. That's enormous for a comet. Most are a few kilometers at best. This is a mountain and island, a mass of tens of billions of tons. It's also moving fast, over 200,000 kilometers per hour relative to the Sun. That velocity isn't unusual for interstellar objects. They need significant speed to escape their home star's gravity and cross the vast distances between systems. But combined with the mass, it represents staggering kinetic energy. And objects that size moving that fast carry another implication. They've been traveling for a very long time. The nearest star system is Alpha Centauri, about 4 light-years away. At 200,000 kilometers per hour, that journey takes roughly 20,000 years. But Three-Eye Atlas didn't necessarily come from the nearest system. It could have originated anywhere in the galaxy, traveling for millions or even billions of years. Think about that timeline, billions of years. While life on Earth evolved from single cells to complex organisms, while continents drifted and mountains rose and fell, while species emerged and went extinct, Three-Eye Atlas was crossing the galaxy. The Sumerians, often credited as one of humanity's first civilizations, emerged around 5,000 years ago. A blink, an instant. In the timescales we're discussing, all of recorded human history is negligible. What does it mean for something to travel that long? What does it mean for an object, natural or otherwise, to exist in the interstellar void for epochs? Longer than the age of any human institution, any city, any written language. It means patience. It means scales beyond our intuition. It means that whatever Three-Eye Atlas is, wherever it came from its journey, represents something older than anything we've ever built or conceived. The ancient Egyptians believed the sky was a goddess nut whose body arched over the earth. Stars were her jewelry. The sun was her eye. And the gods traveled between earth and sky in boats, celestial vessels crossing the heavenly ocean. Perhaps they were closer to the truth than we realize. Perhaps the distinction between myth and observation is thinner than we think, because here, moving through our sky, is an object that has crossed an ocean so vast that light itself requires years to traverse it. A vessel, natural or otherwise, that has journeyed through darkness we cannot imagine, and it has arrived here. now. During the brief window when human civilization developed the technology to detect it, measure it, study it. Coincidence or convergence? There is a cathedral in Chartres, France, built in the 12th century. On the summer solstice at precisely noon, sunlight passes through a special window and illuminates a specific tile on the floor. For centuries, pilgrims have gathered to witness this moment, the alignment of architecture and astronomy, human design resonating with cosmic order. The architects planned this. They understood. Angles knew the sun's path, calculated with stone and glass, how to mark a particular day with light. The alignment isn't random, it's intentional. When we see three celestial objects, Earth, V1 Borisov, and 3I Atlas aligned in space, the question becomes, are we witnessing Chartres Cathedral, or are we simply standing in a field where the sun happens to shine? The mathematics of probability can help us distinguish. Let's consider the geometry. V1 Borisov was discovered on November 2nd, positioned between 3I Atlas and Earth. Its closest approach to Earth occurred on November 11th at a distance of 0.69 astronomical units, about 103 million kilometers. 3I Atlas makes its closest approach to Earth on December 19th at 1.8 astronomical units, approximately 168 million miles. These are not chance alignments from a random observer's perspective. From Earth's vantage point, we see V1 Borisov sitting almost directly along the line connecting us to 3I Atlas, not approximately in the same region of sky, not loosely associated, but geometrically aligned in three-dimensional space, in the vastness of the solar system where objects can be above or below the ecliptic plane by large angles, where distances span hundreds of millions of kilometers, where orbital inclinations vary wildly. This alignment is precise. The probability of any two unrelated objects aligning from Earth's perspective at any given time is already small. The solar system is mostly empty space. Drawing two random objects from this volume and finding them aligned requires specific geometry. But V1 Borisov isn't just any object. It's a comet on a hyperbolic trajectory discovered by the same astronomer who found 2I Borisov appearing at almost the exact moment when 3I Atlas, the most anomalous interstellar visitor ever recorded, was completing its perihelion passage. The timing compounds the improbability. Had V1 Borisov been discovered a month earlier or later, the alignment would be different or absent entirely. Had 3I Atlas arrived a year earlier or later, their paths wouldn't have this relationship. When astronomers calculated the probability of this trajectory configuration occurring naturally, considering the alignment angle, the timing of discovery relative to 3I Atlas's perihelion, the positions at closest approach, they arrived at a figure of approximately 0.05%, 5 in 100,000. Rare, but not astronomically so, until you add it to the other improbabilities. This is where patterns begin to form, where the distinction between coincidence and design becomes philosophically interesting. Ancient observers understood sacred geometry. The Egyptians built pyramids with sides aligned to cardinal directions within fractions of a degree. The Mayans constructed observatories to track Venus with precision requiring centuries of careful measurement. The builders of Newgrange in Ireland created a passage tomb where sunlight penetrates the inner chamber only on the winter solstice. These weren't accidents. They were intentional alignments, human structures harmonizing with celestial mechanics. When we see alignment in nature, we generally assume it's random unless we have reason to suspect otherwise. The planets happen to orbit roughly in the same plane because of how the solar system formed from a rotating disk of material. That's natural alignment arising from physical processes. But when alignment occurs in circumstances that seem too specific, too fine-tuned, the question of intentionality arises. Consider the timing. 3 Atlas reached perihelion on October 29th. During that passage hidden from Earth-based telescopes by the sun's glare, something changed. NASA detected non-gravitational acceleration. The comet was moving in ways that gravity alone couldn't explain. 4 days later, V1 Borisov was discovered. 4 days. The perihelion passage is significant because it's the point of highest velocity and strongest solar gravity. In orbital mechanics, this moment offers maximum efficiency for any maneuver. If you want to change course, if you need to deploy something, if you're optimizing energy usage, perihelion is when you act. The Oberth effect, named after the early rocket scientist Hermann Oberth, describes this principle. A propulsive maneuver is most effective when performed at the point of highest velocity in an orbit. The same amount of thrust produces a larger change in orbital energy. Spacecraft designers use this routinely. When Voyager 2 needed to change course for its grand tour of the outer planets, engineers timed engine burns to coincide with closest approaches to each world. Maximum effect, minimum fuel. If 3I Atlas deployed something during perihelion, if that's what the non-gravitational acceleration represents, then that object would follow a trajectory determined by the velocity and direction imparted at release. And if the release was optimized using the Oberth effect, if it took advantage of perihelion's gravitational environment and velocity, then the deployed object could reach, well, it could reach exactly where V1 Borisov sits now. Speculation. Yes, but testable speculation. The kind that makes predictions we can verify. In the philosophy of science, there's a principle called consilience, the unity of knowledge from different disciplines. When multiple independent lines of evidence point toward the same conclusion, that conclusion gains strength. The geometry points toward intentional positioning. The timing points toward perihelion deployment. The trajectory points toward optimal navigation. The alignment points toward observation. Each piece individually might be explained as coincidence. Together, they form a pattern. The ancient Greeks debated whether the universe was ordered or chaotic. The atomists following Democritus believed in random arrangements of particles. The Platonists believed in mathematical forms underlying reality. The Aristotelians believed in purposeful motion toward natural places. Modern science inherited the atomist view the universe is fundamentally random, and order emerges from statistical processes operating over vast timescales. But when we encounter something that seems ordered, something that displays the signatures of design rather than chance, how do we respond? The conservative response: demand extraordinary evidence. Exhaust all natural explanations. Assume coincidence until proof makes that untenable. The radical response: follow the evidence. If the pattern suggests design, investigate that possibility seriously. Both positions have merit. Both serve important functions in how science progresses. But there's a third consideration articulated beautifully by the philosopher William James. A rule of thinking which would absolutely prevent me from acknowledging certain kinds of truth, if those kinds of truth were really there, would be an irrational rule. In other words, if we establish rules that make it impossible to recognize certain truths, then those rules, however well-intentioned, become obstacles rather than aids to understanding. The geometry is what it is. V1 Borisov sits between 3I Atlas and Earth. The alignment is precise. The timing is significant. The probability is low. We can call it coincidence. We can wait for more data. We can remain appropriately skeptical, but we should also acknowledge what we're looking at: a configuration that, if encountered in human engineering, would immediately be recognized as intentional. 3 points aligned. 3 objects positioned in space with relationships that maximize certain outcomes: observational access, communication paths, strategic positioning. The cathedral at Chartres teaches us that alignment can be designed. The question before us is whether nature alone designed this alignment, or whether something else, some intelligence operating on timescales and with patience beyond our comprehension, positioned these objects with purpose. December 19th approaches. The geometry will become even more precise, and we'll have another opportunity to measure, to observe, to test our hypotheses against reality. Until then, the alignment stands. A pattern in the sky, a configuration too interesting to ignore, too precise to dismiss, too consequential to treat as routine. 3 objects, 3 points of light. And the question that has haunted humanity since we first looked up and wondered, are we alone? The geometry suggests an answer. Whether we're ready to hear it is another matter entirely. There are things in the universe that do not negotiate. Gravity pulls, light travels, entropy increases. These aren't suggestions, they're constraints that define reality as we experience it. And among these certainties, one seemed particularly solid. Comet tails point away from the sun. This happens because of pressure. Not the pressure of atmosphere or water, but the pressure of light itself. Photons carrying momentum, solar wind carrying charged particles. Both push outward from the sun, and when they encounter the gas and dust escaping a comet's nucleus, they drive it backward into the characteristic tail. Every comet humanity has observed for thousands of years follows this pattern. The Chinese called comets broom stars because the tail sweeps behind like bristles. Ancient Romans saw them as cosmic torches, flames trailing as they moved. Medieval Europeans painted them in manuscripts with tails streaming away from the sun. The direction is not negotiable. It's physics, as fundamental as water flowing downhill. Except 3I Atlas decided otherwise. In July and August of 2025, during the early observations after discovery, multiple telescopes reported something strange, a jet of material moving toward the sun. Not away, toward. Initially, some observers suggested it might be an anti-tail, an optical illusion that occurs when Earth crosses through a comet's orbital plane at specific angles. In those geometries, perspective can make it appear as though some dust is moving forward, when it's actually just the projection of material spread along the orbit. Anti-tails are real. They've been documented. They're not common, but they happen. And experienced comet observers know to check for geometric effects before declaring anomalies. So they checked. They calculated the geometry. They compared observations from different locations and viewing angles. And the conclusion was clear: this wasn't an illusion. 3I Atlas was actually producing a jet directed toward the sun. How does this happen? How does material move sunward when all the forces should push it away? There are scenarios, though, none of them are simple. If a comet is rotating in a specific way, and if active venting occurs from regions not directly facing the sun, then jets can point in unexpected directions. Picture a rotating sprinkler. The water doesn't spray straight up, but in patterns determined by the rotation and nozzle orientation. Some comets do this, as they rotate vents open and close, producing jets that curve and angle in complex ways. It requires specific geometry the vent needs to face the right direction at the right time, but it's not impossible. But there's something about directed jets that makes them interesting beyond the pure physics. They represent localized structured activity rather than diffuse random outgassing. They suggest specific regions on the comet's surface are more active than others. They indicate heterogeneity, some parts icy and volatile, others dusty and inert. And in rare cases, directed jets can act as natural rocket engines. If the venting is asymmetric enough, if it produces more thrust in one direction than others, the comet itself can be pushed off course. The momentum of escaping gas transfers to the nucleus, changing its trajectory measurably. This is called non-gravitational acceleration, and it's not unprecedented. Many comets exhibit it, but usually it's subtle, requiring careful analysis to detect. The comet's path deviates slightly from pure gravitational predictions, and astronomers infer that outgassing must be providing a small thrust component. 3I Atlas's non-gravitational acceleration wasn't subtle. NASA measured it at 3. 7 standard deviations. A statistical confidence level that means this is definitely real. The comet was being pushed by something strong enough to significantly alter its trajectory. Strong enough that calculating backwards from the acceleration using momentum conservation suggests the comet lost over 13% of its total mass during the perihelion passage. 13%. Not 1 or 2%, not a fraction within normal cometary activity ranges. 13%, a catastrophic loss, the kind of mass shedding that should produce visible, undeniable evidence. But we'll come to that paradox shortly. For now, consider what the sunward jet tells us about 3I Atlas's behavior. Ancient observers would have been fascinated. They lacked the physics to explain comet tails, but they understood that anomalies mattered. When something in the sky behaved differently than expected, it demanded attention. The Babylonians kept detailed astronomical diaries, recording planetary positions, eclipses, and unusual phenomena. These weren't idle curiosities, they informed decisions, guided rulers, marked significant moments. The sky was a text to be read, and deviations from the expected patterns were significant passages. In medieval Islamic astronomy, observers like al-Battani and Ibn Yunus refined measurements of celestial motions with remarkable precision. They understood that accurate prediction required accounting for perturbations, small deviations from ideal orbits caused by interactions between planets. They didn't have gravitational theory, but they had meticulous observation and mathematical sophistication. What would they have made of a comet that pushed sunward, an object defying the expected pattern? Likely they would have recorded it carefully, noted it as exceptional, and wondered as we wonder now what it signified. The sunward jet isn't the only anomaly in 3I Atlas's behavior, but it's one of the most visually striking. It suggests that whatever is happening on or within this object involves directed processes, structured activity, asymmetric energy release. Natural comets can do this. We've seen it before. But combined with everything else about 3I Atlas, the trajectory, the alignment, the timing, the missing debris cloud, the color, changes the sunward jet becomes another thread in a tapestry that's starting to look less like random weaving and more like deliberate design. In the philosophy of science, there's a concept called underdetermination, the idea that evidence can support multiple theories equally well. Given limited data, we often can't definitively choose between competing explanations. The sunward jet is underdetermined. It could be natural rotation and geometry. It could be unusual composition creating asymmetric outgassing. It could be something we haven't considered. Or it could be controlled venting, directed thrust, propulsion. That last possibility sounds extraordinary. It invites skepticism. As it should, extraordinary claims require extraordinary evidence. But here's the thing about evidence: sometimes it accumulates gradually. Sometimes you don't get a single decisive observation that proves everything. Instead, you get 10 smaller observations, each individually inconclusive, that together paint a picture impossible to ignore. The sunward jet is one such observation, by itself explainable. Added to the pattern, suggestive. The universe is not obligated to make sense to us immediately. It operates according to principles we're still discovering, processes we're still learning to recognize. When we encounter something that doesn't fit expectations, we have two choices: expand our expectations or hold them rigid and force the universe to conform. Science advances when we choose expansion, when we remain open to possibilities that challenge our models. The sunward jet challenges the simple comet model. It suggests 3I Atlas is more complex, more structured, more actively controlled than passive icy bodies tumbling through space. What that means exactly we don't yet know, but the jet points somewhere, and following where it points both literally and metaphorically might lead us toward understanding what 3I Atlas actually is, and whether V1 Borisov sitting between it and Earth serves a purpose in that understanding. Imagine a mountain, not a metaphorical one, but an actual mountain, say Olympus Mons on Mars, the largest volcano in the solar system. A structure so massive it would dwarf Everest, its base, spanning hundreds of kilometers, its peak, reaching into the edge of space. Now imagine that mountain vanishing, not eroding over geological time, but disappearing in a matter of weeks. Every rock, every grain of dust, every ton of material gone. Where did it go? This is the paradox at the heart of 3I Atlas. NASA measured its non-gravitational acceleration. Avi Loeb, director of the Galileo project and former chair of Harvard's astronomy department, calculated what that acceleration means in terms of mass loss. The number is staggering: over 13% of the comet's total mass expelled during the perihelion passage. For an object estimated at tens of billions of tons, 13% translates to more than 5 billion tons of material. 5 billion tons. A mountain, an island. Enough matter to blanket Manhattan under 100 meters of debris. This material didn't vanish. Conservation of mass is not a suggestion, it's a fundamental principle. If 3I Atlas lost 5 billion tons, that mass went somewhere. It should be spreading outward from the nucleus, carried by the velocity of escaping gas, forming a massive visible debris cloud. Comets do this. It's what makes them comets. The fuzzy appearance, the coma, the sweeping tail, all manifestations of outgassed material catching sunlight and glowing across millions of kilometers of space. We should see this debris cloud. It should be impossible to miss. Amateur astronomers with backyard telescopes should be photographing it. Professional observatories should be measuring its size and tracking its evolution, but we don't see it. On November 5th, two observatories, Arnav in Spain and the Virtual Telescope Project in Italy, imaged 3I Atlas post-perihelion. Both captured a compact nucleus surrounded by a modest coma. Fuzzy, yes, clearly cometary in nature, but nothing like the massive debris field that 5 billion tons of expelled material should create. For comparison, on the same day, the Arnav Observatory imaged Comet Lemon, an ordinary member of our solar system's comet population. Lemon displayed a textbook-perfect tail, bright extended, pointing precisely away from the sun as physics demands. Two comets, same telescope, same observation conditions. One looks exactly as expected. The other doesn't. This is the paradox. The acceleration tells us one thing. The observations tell us another. Both can't be right unless something about our understanding is incomplete. Let's walk through the physics carefully, because this is where the mystery becomes undeniable. When gas escapes from a comet, it carries momentum. Momentum is mass times velocity. If a ton of gas leaves the comet at 1 kilometer per second, it carries 1 ton kilometer per second of momentum. Conservation of momentum means the comet must recoil in the opposite direction. Newton's third law: for every action, an equal and opposite reaction. The comet loses mass, and that mass pushes the comet the other way. By measuring how much the comet's trajectory changed, the non-gravitational acceleration, and knowing approximately how fast cometary gas escapes, which depends on temperature and molecular weight, we can calculate backwards to determine how much mass was lost. This isn't speculative mathematics. This is engineering. The same principles that guide rocket design, that let us calculate how much fuel a spacecraft needs to reach Mars, that determine whether a satellite can maintain orbit. The calculation is solid: 5 billion tons minimum. So where is it? The most conservative explanation: the mass did spread out, but in ways that make it difficult to observe from Earth's geometry and with current instruments. Perhaps the outgassing occurred gradually over weeks, rather than in a sudden burst, allowing the material to disperse more thinly, thin enough that the brightness per unit area falls below detection thresholds for ground-based telescopes. Perhaps the gas composition is unusual, dominated by molecules that don't fluoresce brightly in sunlight. Most cometary gas glows because solar UV radiation excites molecules into higher energy states, and they emit light as they decay back down. But if 3I Atlas vents gas that doesn't excite easily, it could remain dark, even while spreading. Perhaps the geometry of Earth's viewing angle makes the debris cloud appear smaller than it is. If the material spread preferentially along the comet's orbital plane, and if we're viewing that plane edge-on, the cloud could be vast but appear compressed. These are all possibilities. They require specific circumstances, unusual composition, fortuitous geometry, observational timing that missed peak activity, but none of them violate physics. Natural comets with strange properties do exist. The universe is large and diverse. Not everything fits tidy categories. This explanation maintains the comet hypothesis. It asks us to accept that 3I Atlas is natural but unusual, and that the missing debris will eventually be detected as observation techniques improve. A more unusual scenario, the mass loss didn't occur through typical outgassing, but through fragmentation. The comet broke apart, shedding large chunks that traveled away on ballistic trajectories. Comets do fragment. We've observed it. Comet Shoemaker-Levy 9 famously broke into multiple pieces before colliding with Jupiter in 1994. Comet 73P Schwarzmann-Wachmann 3 disintegrated into dozens of fragments during close solar passages. Fragmentation produces different signatures than outgassing. Instead of a diffuse cloud, you get discrete objects, smaller nuclei traveling on nearby but distinct orbits. These fragments can be difficult to detect if they're faint or if they're spread far enough apart that surveys miss them. If 3I Atlas shed 5 billion tons as large fragments rather than gas, those fragments might still be out there undetected, traveling through space on paths that will gradually separate them from the main nucleus. This hypothesis has appeal because it explains the missing debris cloud. There isn't one because the mass wasn't vaporized. It stayed solid in chunks too far apart to create a visible structure. But it raises new questions. What caused the fragmentation? Comets break apart due to thermal stress, tidal forces during close approaches, or rotational spin-up. 3I Atlas's perihelion wasn't close enough for extreme tidal stress. Thermal stress could explain it, but usually that creates visible debris, secondary nuclei with their own faint comas, dust clouds from collisions between fragments. We don't see obvious fragmentation signatures, no reports of multiple nuclei, no secondary debris clouds. If fragmentation occurred, it was either remarkably clean or remarkably hidden. The most speculative explanation: the mass loss was neither random outgassing nor chaotic fragmentation, but controlled ejection, directed, intentional. If 3I Atlas is not a natural comet, if it's technological, then the non-gravitational acceleration could represent propulsion, rocket thrust, and the lost mass would be propellant expelled deliberately to change course. Rocket exhaust doesn't hang around forming visible clouds. It disperses rapidly, becoming too diffuse to detect within hours or days. If you watched the space shuttle launch and then looked for its exhaust cloud a week later, you'd find nothing. The gases have mixed with the atmosphere and vanished into background concentration. In space, without atmospheric mixing, gases disperse even faster. The vacuum allows molecules to spread at their thermal velocities kilometers per second until the density becomes immeasurable. If 3I Atlas performed a propulsive maneuver using something analogous to rocket engines, the expelled mass would vanish observationally very quickly. No lingering debris cloud, no tail, just a burst of thrust, then empty space. Alternatively, if the expelled mass was a deployed object, say a probe released during perihelion, it would travel away as a discrete entity. Not a cloud, but a thing, an object with its own trajectory, its own purpose. And if that object happened to be V1 Borisov. This hypothesis explains everything: the acceleration, the missing debris, the timing, the positioning of V1 Borisov between 3I Atlas and Earth. Every observation fits elegantly into a single framework, but it requires accepting that 3I Atlas is artificial,
that we're witnessing technology, not nature, that intelligence from beyond our solar system has arrived, is operating according to principles we can measure but not yet fully understand. That's a large step.
Larger than most scientists are comfortable taking without overwhelming evidence. In ancient alchemy, there was a concept called the mysterium conjunctionis, the mysterious conjunction where opposites unite and transformation occurs. Matter becomes something new. Lead becomes gold. The mortal becomes divine. Modern science abandoned such mysticism, and rightly so. We gained precision, predictability, mathematical rigor, but sometimes the universe presents us with genuine mysteries. Not mystical in the supernatural sense, but mysterious in that our current frameworks don't adequately explain what we observe. The 5 billion tons of missing matter is such a mystery. We have the acceleration. We have the calculations. We have the observations showing the absence of expected debris. Something doesn't fit. Either our understanding of cometary outgassing is incomplete, or our assumptions about what 3I atlases need revision. The conservative approach maintains the comet hypothesis until it becomes untenable. The radical approach consider alternatives seriously even if they challenge foundational assumptions. Both approaches have value. Both have led to scientific breakthroughs. The question is when to transition from one to the other. When does the weight of anomalies become heavy enough that clinging to old models becomes more irrational than exploring new ones? 5 billion tons of matter, gone, invisible, unexplained. The mountain vanished. We measured its disappearance. We just can't find where it went. And that absence, that void where 5 billion tons should be visible, might be the most important data point we have. Because in science, as in detective fiction, sometimes what's missing tells you more than what's present. There are moments when the universe offers opportunities, not randomly, but according to mathematical principles that ancient astronomers glimpsed and modern engineers exploit. Windows in time and space where the same action produces disproportionate results, where efficiency peaks, where what seemed impossible becomes merely difficult. Hermann Oberth understood this. Born in Transylvania in 1894, he became one of the founding fathers of rocketry, publishing calculations showing that space travel was feasible long before anyone had built a rocket capable of reaching orbit. His name attached to a principle that now guides every interplanetary mission, the Oberth effect. The principle is elegant: a propulsive maneuver, a rocket burn, an engine thrust produces greater change in orbital energy when performed at the point of highest velocity in an orbit. The same amount of fuel expended at perihelion rather than aphelion yields significantly larger trajectory changes. Why? Because kinetic energy depends on velocity squared.
When you're moving fast and you add more velocity, the kinetic energy increase is disproportionately large. You're not just adding speed, you're multiplying effect. NASA mission planners use this constantly. When Voyager 2 toured the outer solar system, timing burns to coincide with closest approaches to Jupiter, Saturn, Uranus, and Neptune maximize the gravitational assists received. When New Horizons needed to reach Pluto, a carefully planned Jupiter flyby accelerated the spacecraft far more than its engines alone could manage. The Oberth effect isn't just efficient, it's transformative. It's the difference between missions that are merely difficult and missions that are impossible with current technology. For 3I Atlas, perihelion occurred on October 29th. At that moment, the comet was moving fastest, experiencing maximum solar gravity, positioned at the bottom of the sun's potential well. If something needed to happen, if a maneuver needed to occur, if an object needed to be deployed, if a trajectory needed adjustment, that was the time. 4 days later, V1 Borisov was discovered. 4 days, positioned between 3I Atlas and Earth, following a trajectory that brought it within 103 million kilometers of our planet by November 11th. The timing isn't just interesting, it's optimal. Ancient navigators understood optimal timing instinctively. Polynesian wayfinders cross thousands of miles of open Pacific guided by stars, wave patterns, and intimate knowledge of seasonal conditions. They knew when to depart, when winds would favor certain routes, when currents would aid rather than hinder progress. They didn't have equations, but they had generations of accumulated wisdom. They knew the ocean had rhythms, and successful navigation meant synchronizing with those rhythms rather than fighting them. The Oberth effect is a rhythm of orbital mechanics, a natural pulse in the gravitational landscape. Objects reach perihelion velocity peaks, opportunities open. If you were designing a mission to survey our solar system arriving from interstellar space, with finite resources and no opportunity for resupply, perihelion would be your moment of maximum flexibility. The moment when you could most efficiently alter course, deploy secondary craft, execute maneuvers that would be prohibitively expensive elsewhere in the orbit. This isn't speculation about alien psychology. This is engineering. The math is universal. Any civilization that masters space travel must master orbital mechanics, and orbital mechanics has optimal solutions. The Oberth effect works the same everywhere in the universe, for any object, for any intelligence. If 3I Atlas deployed something during perihelion, the Oberth effect explains why then. Not because of arbitrary choice, but because efficiency and physics aligned.
Let's think through what such a deployment would require. First, timing. You'd calculate your perihelion passage far in advance, months or years before arrival. You'd know the exact moment of closest approach, the velocity at that moment, the gravitational environment. Second, target selection. Where do you want your probe to go? In a multi-planet system like ours, you have options. Inner, rocky planets, gas giants, moons with subsurface oceans. Each requires different trajectories, different deployment velocities. Third, resource allocation. How much delta V change in velocity does each probe need? How many can you deploy given your available resources? How do you maximize coverage while minimizing energy expenditure? The Oberth effect answers some of these questions automatically. Deploy at perihelion, and your probes inherit high velocity. Small adjustments can send them to very different destinations.
The same fuel investment produces widely varying trajectories, allowing diverse exploration with minimal cost. This is how human space agencies approach similar problems. When we design missions to visit multiple targets, we optimize around gravitational assists and orbital mechanics. We don't fight the math, we use it. If 3I Atlas is technological, its behavior during perihelion should reflect these same optimization principles. And what do we observe? Non-gravitational acceleration consistent with mass expulsion. Missing debris cloud consistent with controlled ejection rather than random outgassing. V1 Borisov appearing in the optimal position for Earth observation, arriving at the optimal time given perihelion deployment. Every observation aligns with engineering principles, but nature also has optimal moments, not because of intelligence but because of physics. Perihelion is when comets are most active. Solar heating peaks. Ice sublimates fastest.
Outgassing reaches maximum intensity. If a natural comet were to lose significant mass, perihelion is when it would happen. So the timing alone doesn't prove artificiality. Natural and design scenarios both predict increased activity at perihelion. The question is, what kind of activity occurred? Random chaotic outgassing or controlled directed expulsion? The challenge with this question is that intermediate cases exist. Comets can have active regions, specific spots on the surface where ice is more exposed, where heating is more intense, where venting is concentrated. These jets can appear directed even though they arise from natural asymmetries in the nucleus. Telling the difference between directed because of natural geometry and directed because of intentional design requires detailed observation. We need to see the surface structure map the active regions, watch how activity changes with rotation and solar distance.
For 3I Atlas, we don't yet have that level of detail. The object is too far, too faint, too small to resolve surface features with current telescopes. The Mars Reconnaissance Orbiter captured high-resolution images during the October flyby, but NASA hasn't released them. Europa Clipper may have collected data during its passage through the ion tail, but again, no public release. We're left inferring from indirect measurements. Acceleration without visible debris, timing that aligns with optimal deployment windows, positioning that maximizes observational opportunities. Inference is not proof, but it's what we have. And the pattern of inferences taken together suggests something remarkable is occurring. In 1610, Galileo turned his telescope toward Jupiter and saw 4 moons orbiting the giant planet. This observation shattered the prevailing model that all celestial objects orbited Earth.
If Jupiter had its own moons, if multiple centers of motion existed, then the Earth-centered cosmos couldn't be correct. The observation was simple: 4 points of light near Jupiter, changing position night after night. The inference was revolutionary. These were worlds orbiting another world, proving that not everything revolved around us. Could Galileo have been wrong? Could those lights have been something else? Background stars? Artifacts? Illusions? Technically, yes, but the pattern was too consistent, the motion too regular, the explanation too elegant. Within a generation, no serious astronomer disputed Jupiter's moons. We stand at a similar moment with 3I Atlas. The observations are clear: anomalous acceleration, missing debris, optimal timing, suggestive positioning. The inference is revolutionary. This might not be natural. History teaches that revolutionary inferences, when backed by consistent observations, eventually become accepted truths.
The question is how long the transition takes and how much resistance emerges before acceptance. The Oberth effect is not controversial. It's textbook physics used by every space agency, verified by every mission that exploits gravitational assists. What's controversial is suggesting that something might be using it right now in our solar system for purposes we can only hypothesize. But controversial doesn't mean wrong. Sometimes the controversial idea is the correct one, waiting for the weight of evidence to shift consensus. Perihelion was October 29th. The optimal moment came and went. Whatever happened, natural or designed, occurred when physics and geometry aligned to permit it. And now we watch the aftermath. V1 Borisov between us and 3I Atlas, December 19th approaching. Another convergence, another optimal moment for observation. The universe offers opportunities. Whether we're witnessing natural processes taking advantage of those opportunities or intelligence doing the same, the elegance remains. Sometimes the line between natural and designed is clearer than we think. Sometimes it's razor thin, and sometimes, as now, we don't yet know which side of that line we're standing on. Color is information. This truth spans from the ancient use of pigments in ritual to the modern analysis of starlight split into spectral components. When something changes color, physics demands an explanation. Temperature shift, chemical reaction, energy state transition. Something changed and the color reveals what? 3I Atlas turned blue, not metaphorically. Not in false color images designed to highlight specific wavelengths. The object developed a distinctly blue hue during and immediately after its perihelion passage, observable in photometric data collected by spacecraft and ground-based instruments monitoring its solar approach.
Blue light consists of shorter wavelengths, higher frequency photons than the reddish or neutral tones typical of cometary dust and gas. This matters because it tells us about the processes generating the light. This was the third documented color shift since 3I Atlas's discovery in July. 3 changes. 3 distinct alterations in the spectral signature of an object that, if natural, should remain relatively constant in color unless dramatic composition or activity changes occur. Normal comets do change color subtly as they approach the sun. Different ices sublimate at different temperatures. Water ice, at one threshold, carbon dioxide at another, carbon monoxide at yet another. As solar heating intensifies, the mix of gases changes, and the color shifts accordingly. But these changes are gradual, predictable, and generally remain within a narrow range. Comets typically appear greenish from excited carbon molecules or reddish from dust reflecting sunlight. Blue is unusual,
Blue suggests something different is happening. For a natural comet, blue coloration most likely comes from ionized carbon monoxide. When intense ultraviolet radiation from the sun strips electrons from CO molecules, the resulting ions emit blue light as electrons recombine. This is known physics observed in other astronomical contexts. If 3I Atlas vented massive amounts of carbon monoxide during perihelion, and if solar radiation ionized that gas extensively, the blue glow would result naturally. No mystery, just chemistry and atomic physics operating as expected. But here's the challenge: producing visible blue glow requires substantial gas emission, enough CO to dominate the spectral signature, enough ionization to make the emission bright enough to detect. That much gas should create a debris cloud, a visible coma and tail. The very thing we've established is missing from post-perihelion observations.
So either the blue color comes from CO ionization, which demands gas emissions we don't observe, or it comes from something else. Avi Loeb raised the alternative carefully. The blue color could potentially be explained by a hot engine or a source of artificial light. Hot engine, artificial light. These phrases carry implications that make institutional astronomers uncomfortable. But let's examine them objectively as hypotheses to be tested rather than heresies to be dismissed. Engines glow. Rocket exhausts burn blue when combustion temperatures are high enough. The space shuttle's main engines produced a brilliant blue-white flame visible for hundreds of kilometers. Jet engines at full thrust glow internally with blue-hot combustion. This happens because of blackbody radiation. Heat an object sufficiently and it emits light. The color depends on temperature. Red heat is cooler. White heat is hotter. Blue-white heat is hotter still. If 3I Atlas contains propulsion systems, if it operated engines during perihelion, those engines would emit thermal radiation. Depending on the propellant and combustion temperature, that radiation could appear blue. Ion drives, which use electromagnetic fields to accelerate charged particles, emit blue light directly, not from heat, but from the glow of ionized propellant. Dawn spacecraft, which orbited the asteroid Vesta and dwarf planet Ceres, used ion propulsion that glowed electric blue during operation. Nuclear thermal rockets, where propellant passes through a reactor core and expands at extreme temperatures, would produce intense blue-white exhaust. Any sufficiently advanced propulsion operating at high power output could produce blue emissions as a byproduct. This remains speculative. We have no direct evidence of engines. But the hypothesis fits the observations: blue coloration appearing during perihelion, coinciding with non-gravitational acceleration, lacking the expected gas emissions that natural processes demand. Alternatively, blue light could come from non-thermal sources. LEDs emit narrow spectral lines. Plasma discharges glow blue. Arc welding creates intense blue-white light from electrical ionization. If 3I Atlas carries instruments that use light for communication sensing or energy transmission, and if those instruments operated during perihelion, they could produce blue emissions detectable by spacecraft monitoring from a distance. This seems exotic, but consider human spacecraft carry lights. Communication systems use lasers. Sensors emit and detect electromagnetic radiation across multiple wavelengths. If we sent a probe to another star system, it would carry similar systems. And if beings there observed our probe, they might detect emissions that didn't fit natural comet behavior. Would they assume those emissions were artificial, or would they strain to explain them naturally, reluctant to make the leap toward intelligence?
Ancient cultures paid careful attention to celestial colors. Chinese astronomers categorized comets by hue: white comets, red comets, yellow comets. Each color carried different significance, informed different interpretations. This wasn't superstition, it was empirical observation. Different comets do appear different colors based on composition and activity level. The Chinese records demonstrate that careful observation over centuries yields genuine insights. Blue comets are rare in historical records, not absent but uncommon enough to be noteworthy when they occur. In mythology, blue often associates with transformation and otherworldliness. The Egyptian god Amun was depicted with blue skin, signifying his cosmic nature. Hindu depictions of Krishna show him blue-skinned, representing divine transcendence. The Virgin Mary wears blue robes in Christian iconography, symbolizing heaven and purity. Blue is the color of sky and deep water elements that separate terrestrial from celestial, that mark boundaries between the earthly and the numinous. When 3 Atlas turns blue, it participates in this ancient symbolism, whether intentionally or not. It becomes liminal boundary crossing, neither fully of nature nor fully explained by it. Accompanying the blue shift was a dramatic brightening. 3I Atlas increased in brightness by a factor of approximately 5 in the green spectral band during its perihelion passage. Factor of 5, not a subtle change, a dramatic surge. Comets brighten as they approach the sun. This is expected. Solar heating increases activity, intensifies, more light gets reflected and emitted. But the increase should be smooth, following power laws based on distance and solar flux. Sudden jumps suggest something changed abruptly. Something activated, intensified, began operating at a different level. Natural explanations exist. Ice can suddenly crack, exposing fresh volatile material to sunlight. Landslides on the nucleus can unveil pristine ice never before touched by solar radiation. These outburst events happen occasionally, creating temporary brightness surges, but outbursts typically fade quickly. Within hours or days, the exposed ice gets covered with dust again, and brightness returns to normal levels. 3I Atlas's brightness increase persisted through and beyond perihelion, suggesting sustained activity rather than a transient event. Artificial systems change state abruptly all the time. Power systems switch on. Instruments activate. Navigation beacons light up. If 3I Atlas contains onboard systems that powered up during perihelion, taking advantage of maximum available solar energy, or executing programmed operations, a sudden brightness increase makes perfect sense. By itself, the blue coloration is interesting, but not conclusive. Natural processes can produce it. Added to the missing debris cloud, the non-gravitational acceleration, the sunward jet, the optimal timing, the geometric alignment with V1 Borisov, it becomes part of a pattern. Each anomaly can be explained individually with sufficient creativity, but explaining all of them together while maintaining the natural comet hypothesis requires increasingly contorted reasoning. At some point, the simplest explanation becomes, this is not a typical comet. This is something else. What that something else is, whether an unusual natural object with properties we haven't encountered before, or a technological artifact, remains open. But the blue transformation adds another data point that doesn't fit comfortably in the standard model. In ancient alchemy, color changes signified transformation stages.
The great work proceeded through phases: nigredo, blackening; albedo, whitening; citrinitas, yellowing; rubedo, reddening. Each color marked progress toward the philosopher's stone, toward transmutation, toward perfection. Modern chemistry abandoned this symbolic framework, recognizing that color changes reflect electron transitions and molecular rearrangements. Objective, measurable, predictable. But the instinct was sound. Color change indicates change of state. Something fundamental altered. 3I Atlas turned blue at perihelion. Whether that reflects natural chemistry or artificial operation, it marks a transition. From what to what, we don't yet fully understand. But the color lingers in the data. A blue glow at the moment of maximum solar approach, a hue that shouldn't dominate without gas emissions we don't detect, a shade suggesting heat energy processes operating at intensity levels that strain natural explanation. The universe is not obligated to declare its nature clearly. Sometimes it whispers. Sometimes the whisper comes in unexpected colors, forcing us to question what we think we know about the objects passing through our cosmic neighborhood. Blue. The color of transformation, the color of the void between stars. The color Three-Eye Atlas chose to wear at the very moment when, according to engineering principles, any advanced system would execute its most critical operations. Coincidence, natural chemistry, or something more deliberate? The answer waits in data yet to be collected, in observations yet to be made. But the question has already been asked. And once asked, it cannot be unasked. Before telescopes, before photography, before spectrographs and computer models, humans watched the sky with naked eyes and remarkable dedication. What they saw, recorded, and pondered laid foundations for astronomy as a science and raised questions that echo still. In ancient Mesopotamia, along the fertile valleys of the Tigris and Euphrates, Babylonian astronomers maintained detailed records spanning centuries. Clay tablets preserved in cuneiform, script document planetary positions, lunar eclipses, and unusual phenomena with precision that staggers modern researchers. These weren't casual observations. They were systematic intergenerational projects. Knowledge accumulated over lifetimes, passed from master to student, refined through patient watching. The Babylonians knew how to predict eclipses. They understood that celestial patterns repeated on cycles, the Saros cycle for eclipses spanning 18 years, the Metonic cycle for lunar phases spanning 19 years. They couldn't explain why these patterns existed, but they recognized them and used them. Comets appeared in their records too. Hairy stars that moved against the fixed background, trailing luminous banners. Each appearance was noted: position, duration, brightness, direction of tail. Some comet passages coincided with significant historical events, and scribes recorded both, leaving later scholars to debate whether the association was causal or coincidental. Across the Pacific, Mayan astronomers achieved comparable sophistication without any contact with Old World cultures. Their observatories, aligned to track Venus and other celestial bodies, enabled them to calculate that planet's synodic period, the time between similar configurations relative to Earth and Sun, to within hours over centuries. The Dresden Codex, one of the few surviving Mayan books, contains tables predicting Venus appearances with accuracy that wouldn't be matched by European astronomy until the Renaissance. They understood cycles. They mapped time against celestial motion. And they watched for anomalies, anything that deviated from expected patterns. In Egypt, priests aligned temples to stellar and solar events with geometric precision that required accurate measurement and long-term observation. The pyramids at Giza aligned to cardinal directions within fractions of a degree. The temple at Abu Simbel allows sunlight to penetrate its inner sanctum only on the pharaoh's birthday. These weren't accidental. They demonstrate understanding of Earth's orientation relative to celestial references and the ability to translate that understanding into monumental architecture. What interests us now is not just that these cultures watched the sky, but what they saw and how they interpreted it. Ancient texts describe unusual celestial phenomena. The Egyptian pyramid texts reference stars and divine boats traveling between earth and sky. Sumerian myths speak of the Anunnaki beings who descended from the heavens, bringing knowledge and civilization. Literally interpreted, these are fantastic claims, God's visitors, beings from other realms. Dismissed by modern scholarship as mythology, symbolic narratives expressing cultural values rather than historical accounts.
But what if some of these stories preserve memories of genuine observations, not gods, but objects in the sky that behaved unusually? Visitors in the astronomical sense, interstellar objects passing through the inner solar system visible to dedicated sky watchers, interpreted through the conceptual frameworks available at the time. We have no way to verify this directly. The past doesn't leave data files, but the possibility is worth considering, especially now as we observe objects that challenge our own interpretive frameworks. The question of whether other worlds exist and whether they might be inhabited is not modern. Ancient Greek philosophers debated it extensively. Democritus and Epicurus argued for infinite worlds arising from atomic combinations. If atoms are infinite and space is infinite, they reasoned, then countless worlds must form some resembling ours, others entirely different. Aristotle disagreed. He argued for a single cosmos with Earth at the center. The heavens were perfect crystalline spheres carrying planets and stars. Nothing beyond existed. The universe was finite, bounded, unique. For centuries, Aristotelian cosmology dominated. The Church adopted it, making geocentrism a matter of religious doctrine. To question it was to question divine order. Giordano Bruno challenged this in the late 1500s. He argued for infinite worlds, infinite stars, infinite opportunities for life and intelligence. The universe, he claimed, was far vaster and more populated than theology allowed. His reward was to be burned at the stake in 1600. 8 years later, Galileo's telescope vindicated some of Bruno's intuitions. Jupiter had moons. Other centers of motion existed. The Earth-centered model crumbled. Within a generation, the plurality of worlds shifted from heresy to mainstream speculation. By the 1700s, serious thinkers assumed the moon planets, even the sun, might harbor inhabitants. Not based on evidence, they had none, but on philosophical reasoning that such vast spaces would not be wasted. The pendulum swung back in the 1800s as spectroscopy revealed that most planets were hostile to life as we knew it. Venus was too hot, Mars too cold, Jupiter gaseous. The moon lacked atmosphere. Slowly, the populated cosmos shrank back to Earth alone. The exoplanet revolution of the past 30 years swung the pendulum again. We now know most stars have planets. Thousands have been confirmed, with estimates suggesting hundreds of billions in our galaxy alone. The question shifted from, are there other worlds, to, are any of them inhabited? And more specifically, if they are, have any achieved technological civilization, and if so, might they explore as we do? This is the context in which 3i Atlas appears. Not as an isolated anomaly, but as the latest development in humanity's long conversation with the cosmos about whether we're alone. Imagine being a Babylonian astronomer 3,000 years ago. You know the stars, their positions, their movements. You can predict eclipses. You track planets with precision. And then one night something new appears. A fuzzy star that wasn't there before. It moves not like planets on their predictable circuits, but irregularly following paths you can chart but not yet explain. You watch it for weeks. You measure its position each night. You see the tail develop, stretching away from the sun. You note when it's brightest, when it fades, when it finally disappears beyond your ability to track. You record all this on clay tablets, knowing future astronomers will reference your observations. What did you see? A comet, we'd say now. A natural object following orbital mechanics. But if that comet behaved unusually, if it accelerated without visible outgassing, if it deployed smaller objects, if it exhibited characteristics that didn't fit normal patterns, would you notice? Would you describe it differently? Would your records preserve that strangeness for millennia? We'll never know for certain. Ancient records are fragmentary translations, uncertain cultural contexts, alien to modern readers. What seems mythological might encode observations. What seems observational might be embellished mythology. But the possibility lingers. Maybe we're not the first generation to wonder about unusual visitors.
Maybe ancient peoples saw objects like 3-Eye Atlas and V1 Borisov, interpreted them through the frameworks available, gods, omens, celestial boats, and left us fragments we're only now learning to read correctly. One lesson history teaches clearly: each generation believes itself uniquely positioned to understand reality, only to have subsequent generations reveal how incomplete that understanding was. Ancient astronomers believed Earth was the center. Copernicus moved us to orbit the sun. Galileo found other centers of motion. Hubble discovered the universe is far larger than our galaxy. And still we learn that our assumptions were provincial. Perhaps our assumption that interstellar visitors must be natural, must be comets and asteroids and inert matter. Perhaps that assumption will prove equally provincial. Perhaps we're as wrong as Aristotelians believing Earth was the universe's center. The universe doesn't care about our comfort. It simply is.
And revealing its nature requires humility. The willingness to admit our frameworks might be incomplete. Ancient peoples had that humility. They knew they didn't understand everything. They built their knowledge slowly testing observations against traditions willing to refine and adjust. Modern science inherits that tradition, but sometimes institutional science forgets the humility part. Sometimes we become so invested in current models that contrary evidence gets dismissed rather than investigated. 3-Eye Atlas challenges our models. V1 Borisov challenges them further. The pattern of anomalies forces us to choose, defend the comfortable or explore the uncomfortable. History suggests exploring usually wins eventually. The question is how long resistance delays discovery and what opportunities are missed during the delay. Ancient skies held mysteries. Some were solved eclipses, planetary motion, stellar parallax.
Others remain ball lightning, atmospheric anomalies, rare celestial events recorded once and never again. Our skies hold mysteries too, and one of them moving through our solar system right now might be the most significant mystery humanity has ever encountered. Whether we're ready to acknowledge that is another question. On October 2nd and 3rd, 2025, the Mars Reconnaissance Orbiter turned its high-rise camera toward 3-Eye Atlas. The interstellar visitor was passing within 29 million kilometers of Mars, close enough that the spacecraft's instruments could capture unprecedented detail, better resolution than any Earth-based telescope could achieve, even Hubble. 3 times sharper, 3 times more revealing. The images exist. They sit in NASA's servers, backed up, preserved, cataloged. They show the surface of the most anomalous object ever observed by human technology at a resolution capable of detecting structures, patterns, anything that might confirm or deny the hypotheses swirling through astronomical communities worldwide. No one has seen them. Not the public, not most scientists. Not even astronomers who've spent months studying 3-Eye Atlas, who've written papers about its behavior, who desperately need this data to test their models. NASA has not released the images. The agency cites the October 1st government shutdown. Funding lapsed. Non-essential personnel were furloughed. Data processing pipelines froze. Public communications ceased. Technically accurate, practically suspicious. Because NASA has a history with public disclosure, a complicated history, sometimes exemplary live streaming missions releasing images within hours, maintaining transparency that sets global standards. Sometimes opaque delays, redactions, information siloed behind security classifications or administrative barriers. The question is whether this particular delay represents routine bureaucracy or something more calculated. Whether the shutdown excuse is genuine or convenient. Whether we're witnessing standard procedure or deliberate obstruction. Let's examine what we know. The high-resolution imaging science experiment HiRISE is one of the most powerful cameras ever sent to another planet. Its 50-centimeter aperture can resolve features as small as 30 centimeters across on Mars's surface from orbit. pointed at 3I Atlas during the close approach, it achieved approximately 30 kilometers per pixel. For context, Hubble Space Telescope's best image of 3I Atlas captured on July 21st achieved about 90 kilometers per pixel. HiRise's resolution is 3 times better. 3 times better means 3 times more detail. The difference between seeing a blurry blob and seeing structure,
between uncertainty and clarity. At 30 kilometers per pixel, you can detect whether the nucleus is round or elongated, smooth or fractured. You can spot jets emerging from specific locations. You can identify rotation through brightness variations across the surface. You can measure reflectivity properties that indicate composition. You can, in short, answer many of the questions that currently remain unanswered because Earth-based observations lack sufficient resolution. The images were captured over 30 months ago. Standard processing for HiRise data takes days to weeks, not months. Calibration noise, reduction, geometric correction, all routine procedures with established pipelines. By mid-October, the images should have been ready for scientific analysis. By November, ready for public release. By now, they should be studied, published, integrated into the ongoing investigation of 3I Atlas's nature. They remain unreleased. The U.S. federal government shut down on October 1, 2025 due to congressional failure to pass budget appropriations. Non-essential operations ceased. Employees were furloughed without pay. Services stopped. NASA was affected. Headquarters reduced to skeleton staff. Mission control continued for spacecraft. You can't just turn off satellites in orbit, but everything else paused. Does this explain the HiRise delay? Partially. Data processing does require personnel. If the people authorized to release images were furloughed, the images stay locked behind bureaucratic procedures. But here's what strains credulity. Other NASA missions continued flowing data. James Webb Space Telescope released images. Hubble maintained its observation schedule. Mars rovers sent back photographs. Europa Clipper transmitted telemetry. Somehow, the shutdown affected only specific data streams. Specifically those data streams that might answer the most controversial questions about the most significant astronomical object currently in our solar system. Avi Loeb addressed this directly. He wrote that we should not hold science hostage to shut down politics. He emphasized that the scientific community would greatly benefit from this time-sensitive data. Time-sensitive because 3I Atlas is moving, receding, becoming harder to observe with each passing day. Coordinating follow-up observations requires knowing what HiRise saw. Without that information, astronomers work blind, wasting precious telescope time on redundant measurements while critical data goes uncollected. On October 31st, Representative Anna Paulina Luna from Florida sent a formal letter to NASA's acting administrator. She requested immediate release of observational data related to 3I Atlas, including the HiRise images. Her letter was professional but firm. She noted that this information is of great importance to advancing our understanding of interstellar visitors. She implied, though didn't explicitly state, that national security implications exist when unknown objects transit our solar system. Luna didn't write this letter casually. She consulted with Avi Loeb beforehand, understanding that political pressure carries weight, scientific requests don't. In a functional democracy, Congress oversees executive agencies. When NASA withholds information, congressional intervention is appropriate. On November 5th, Luna posted an update. She'd had a good conversation with NASA. The agency would release images and data as soon as the government reopened. Unfortunately, bureaucratic reasons prevented release until then. That was 3 weeks ago. The government has since reopened. The bureaucratic reasons should have dissolved. The images remain unreleased. The European Space Agency faced no shutdown. Its missions, Mars Express ExoMars Trace Gas Orbiter, attempted to photograph 3I Atlas during the same October flyby window. ESA captured 488 images. They released two out of 488, less than 0.5%. The released images show 3I Atlas as a fuzzy white dot. Useful for confirming its position but revealing little about structure or activity. The other 486 images remain locked in ESA's archives unexplained. Why ESA hasn't said? No official statement, no technical justification, no timeline for future release. The pattern mirrors. NASA's capture extensive data release, minimal information, stay silent about the rest. In contrast, the China National Space Administration released images from the Tianwen-1 Mars orbiter on November 6th. The images show 3I Atlas's nucleus surrounded by a coma spanning 5,000 to 10,000 kilometers. CNSA acknowledged the technical challenge. Photographing a distant, faint target required careful navigation and instrument operation. But they did it. They succeeded. And they shared the results. No delays, no bureaucratic excuses. Just science operating as it should observe. Analyze, publish, contribute to collective understanding. Why can China's space agency release data, while NASA and ESA cannot? The obvious answer: they choose to. Whatever constraints affect Western agencies don't apply to CNSA. Or perhaps CNSA leadership decided transparency serves their interests better than secrecy. The missing high-rise images prevent specific testable analyses. First, structural assessment. Is 3I Atlas a single cohesive body or a loosely bound rubble pile? Solid objects and loose aggregates behave differently under rotation and thermal stress. Imaging can distinguish them. Second, surface features. Are there jets? Active regions, geometric patterns that might indicate artificiality, or irregular surfaces typical of natural comets? Third, rotation measurement. Brightness variations across multiple images reveal rotation period. Combined with shape, this constrains models of internal structure and composition. Fourth, the missing debris cloud. High-rises sensitivity might detect faint material that ground-based telescopes miss. If 5 billion tons of expelled matter spread diffusely, higher resolution might capture what lower resolution can't. Each of these analyses either supports or challenges the natural comet hypothesis. Collectively, they could resolve the question of what 3I Atlas actually is. By withholding this data, NASA prevents that resolution. Whether intentionally or through bureaucratic inertia doesn't change the effect. Uncertainty persists when clarity is possible. In the absence of information, speculation flourishes. Some observers assume deliberate suppression. They argue NASA knows something disturbing, something that would trigger public panic or institutional embarrassment. Others assume incompetence.
Bureaucracies move slowly. Priorities conflict. The shutdown genuinely disrupted operations, and restoring normal function takes time. Both perspectives have precedent. NASA has suppressed information, national security, international agreements, and internal politics all provide motives. NASA has also simply been slow, understaffed, overwhelmed, not prioritizing public engagement. Distinguishing between suppression and incompetence requires inside knowledge we don't have. What we can observe is the effect crucial data remains hidden, while the object it depicts recedes beyond the range where follow-up observations remain feasible. Trust erodes when institutions withhold information, when official explanations seem incomplete, when patterns of delay appear non-random. NASA's reputation depends on public trust. The agency requests billions in taxpayer funding annually. That funding requires congressional approval, which depends on public support.
Eroding trust jeopardizes funding, jeopardizes missions, jeopardizes NASA's ability to function. So why risk it? Why invite suspicion by withholding data that, if innocuous, would strengthen the natural comet hypothesis and quiet speculation? Either the data is innocuous and bureaucracy delays it pointlessly, or the data is significant, and someone decided public disclosure carries costs that outweigh benefits. We cannot know which without seeing the images.
That's the frustration. That's the bind. We're left inferring motivations from absences, guessing at what hides behind procedural barriers. What we know for certain images exist. 30 kilometers per pixel. Unprecedented detail. Answers waiting in digital files on NASA servers. And those answers remain locked away while December 19th approaches, and the window for understanding this visitor, perhaps the most important visitor humanity has ever hosted, continues closing. The ancient library of Alexandria burned, thousands of texts lost, knowledge that might have accelerated human progress by centuries had vanished. We don't face fire now, we face bureaucracy. But the effect is similar. Information that could change our understanding sits inaccessible, wasted while time runs out. Someone has seen those images. Someone knows what they show. Someone decided the world doesn't need to know yet. The question is why, and whether when the images finally emerge, if they emerge, they'll confirm our comfortable assumptions or shatter them beyond repair. There's a spacecraft traveling between Earth and Jupiter right now. Europa Clipper, launched in October 2024, beginning a journey to study Europa's subsurface ocean and assess the moon's habitability. It carries sophisticated instruments designed to analyze composition, magnetic fields, and plume activity. And between October 30th and November 6th, 2025, it flew directly through the ion tail of 3I Atlas. No press release, no announcement,
No data shared. Just silence. This is extraordinary for several reasons. When comets approach the sun, they develop two tails. The dust tail curved and bright forms as solar radiation pressure pushes dust particles away from the nucleus. The ion tail straight and often fainter forms as solar wind strips electrons from gas molecules and carries the charged particles radially away from the sun. Ion tails are narrow and fast. The particles travel at hundreds of kilometers per second, stretched along magnetic field lines into structures that can extend millions of kilometers. 3I Atlas developed an ion tail. Multiple observations confirmed it, and Europa Clipper's trajectory intersected that tail during the early November window. This is unprecedented. No human spacecraft has ever sampled material from an interstellar object in situ. All previous observations have been remote-looking, from Earth or from distant orbits, analyzing reflected and emitted light.
In situ means being there immersed, measuring directly. Europa Clipper carries instruments perfect for this opportunity. MassSpec's mass spectrometer for planetary exploration measures composition at the molecular and atomic level, can identify specific molecules, isotopic ratios, chemical states, exactly what you'd want for determining whether interstellar material differs from solar system material in detectable ways. Pseudo-surface dust. Analyzer measures composition, size, velocity, and impact properties of dust particles. Can detect tiny grains moving at high speeds, the kind ejected from 3I Atlas during outgassing or released during fragmentation. Magnetometer maps. Magnetic field structures with high precision. Ion tails have characteristic magnetic signatures. Any internal magnetic field from 3I Atlas itself would contribute to the structure in ways MAG could detect. All three instruments operate during cruise phase. They're not idle until Jupiter arrival. They collect data on the solar wind, interplanetary dust, magnetic environment, everything the spacecraft encounters en route, which means they collected data on 3I Atlas's ion tail. They measured it. They recorded composition, particle fluxes, magnetic properties. All the information needed to determine whether this interstellar visitor differs compositionally from solar system comets. NASA has released none of this data. Europa Clipper launched on October 14, 2024. Its trajectory arcs outward from Earth toward Jupiter, following a path that takes advantage of gravitational assists and optimal orbital mechanics. 3I Atlas reached perihelion on October 29, 2025. At that moment, it was developing its ion tail venting material that streamed away from the nucleus along the solar wind. Geometry brought their paths together. Between October 30th and November 6th, Europa Clipper traveled through the region of space where 3I Atlas's ion tail extended. Not a chance encounter, both trajectories were determined months in advance. Mission planners knew the opportunity existed. The question is whether they plan to exploit it. In principle, targeting specific science objectives during cruise phase is common. Instruments get calibrated, test observations verify performance. If an interesting target appears along the path, mission teams might adjust pointing or observation schedules to collect bonus data. But 3I Atlas isn't just interesting. It's potentially the most significant astronomical object under current study. Any data collected during the tail transit would be scientifically valuable, publishable, likely to generate significant interest. So why the silence? Why no announcement that Europa Clipper collected this data? Why no preliminary results? No press release, no acknowledgement that the encounter even occurred? Europa Clipper flew through the ion tail and detected exactly what you'd expect from a comet. Water group ions, carbon dioxide, carbon monoxide. Abundances consistent with natural ice sublimation. Isotopic ratios typical of solar system material or within expected ranges for interstellar comets. Nothing unusual, nothing that challenges the natural hypothesis. Just confirmation that 3I Atlas behaves like a comet, even if an anomalous one in some respects. If this is the case, releasing the data would strengthen NASA's position. It would provide direct evidence supporting their statements that 3I Atlas looks like a comet does comet things. It would quiet speculation, reassure the public, demonstrate transparency. So why not release it? Bureaucratic inertia. The shutdown delayed processing. The data requires thorough analysis before publication. Papers need peer review. Standard science takes time. This explanation is reasonable. It requires no conspiracy, no cover-up, just the slow grinding of institutional machinery, but it doesn't explain complete silence. Even during shutdowns, NASA has managed to release basic status updates. Europa Clipper operating nominally, data collection ongoing, analysis underway. A single tweet would suffice. Instead, nothing, as if the encounter didn't happen. As if nobody thought to mention that our newest flagship mission just sampled interstellar material for the first time in human history. Perhaps the instruments detected unusual signatures, nickel abundances higher than expected, particle compositions that don't fit standard cometary models, magnetic field structures suggesting internal activity. But the data is noisy, preliminary, incomplete. Releasing it now invites misinterpretation. Better to wait, calibrate thoroughly, cross-check against the laboratory standards, ensure the findings are solid before making public statements. This is a defensible scientific position. Premature announcements damage credibility when they unravel under scrutiny. Better slow and correct than fast and wrong.
However, 3I Atlas is time-sensitive. The object is leaving. Ground-based observations become more difficult daily. Other missions might benefit from knowing what Europa Clipper detected, allowing them to adjust their own observation plans. Withholding even preliminary findings hinders the broader scientific effort. It prioritizes individual mission teams' publication rights over collective progress. The most speculative scenario, Europa Clipper detected something that cannot be easily explained naturally. Unambiguous evidence of industrial materials, exotic isotopic ratios impossible to produce in normal stellar environments, magnetic field signatures indicating internal power sources, particle compositions that have no business in a pristine comet from the outer reaches of another star system. If this is what the data shows, NASA faces an impossible decision.
Release it and trigger global upheaval. Economic instability, religious crises, psychological disruption as humanity grapples with confirmed evidence of extraterrestrial technology. Or withhold it. Hide behind procedural excuses, control the narrative until some undefined future moment when leaders decide civilization is ready for the truth. This interpretation assumes much. It requires not just anomalous data, but unequivocal data. It requires NASA to believe the evidence is strong enough that public disclosure would be catastrophic. And it requires a conspiracy of silence, not just at NASA, but among everyone with access to the data. Scientists, engineers, administrators, all maintaining secrecy about the most significant discovery in human history. Possible technically, likely harder to assess. Large conspiracies are difficult to maintain. People leak, whistleblowers emerge. Conscience and curiosity overcome institutional loyalty. Yet the silence persists. No leaks.
No whistleblowers. No rival analysis teams publishing contradictory findings based on stolen or independently acquired data. Either the data truly is routine or information control is more effective than cynics assume. Europa Clipper's unreleased tail transit data fits a broader pattern. High-rise images unreleased. ESA's 486 additional images unreleased. Detailed compositional analysis from ground-based spectroscopy sparse and delayed. Individually, each delay might have innocent explanations. Collectively, they form a structure of opacity that invites suspicion. Why do multiple independent agencies and missions all withhold data about the same object? Why does information flow slowly when urgency exists? Why does bureaucracy suddenly become omnipotent precisely when transparency matters most? Maybe these are the wrong questions. Maybe asking why the conspiracy presumes conspiracy where none exists.
Maybe the simpler answer is systemic dysfunction agencies that prioritize internal politics over external communication, that default to secrecy out of habit, that lack coordination and clarity. But even dysfunction this consistent starts looking like policy. In an ideal world, NASA would have announced the Europa Clipper tail transit in advance. Our spacecraft will pass through 3I Atlas's ion tail during early November. We plan to collect composition data, preliminary results expected within days. Then after the encounter, Europa Clipper successfully sampled interstellar material. Initial analysis shows whatever they found. Full data release, pending detailed calibration, papers in preparation. Transparency, communication, science as public endeavor rather than classified intelligence. Instead, we get silence. And silence, especially now, says more than words. The universe offers rare opportunities. Europa Clipper's path intersecting 3I Atlas's ion tail is one such opportunity. A convergence we couldn't have planned if we tried. The interstellar visitor arrived when a capable spacecraft happened to be traveling through the right region of space. Wasting that opportunity by locking data behind administrative barriers is frustrating, scientifically wasteful, potentially catastrophic if the data could inform December 19th observations but remains hidden until after that critical date passes. Someone has seen the Europa Clipper data. Someone knows what was detected. And someone decided we don't need to know. The reasons might be innocent. The reasons might be sinister. Without access, we can't judge. What we can observe is the absence. The void where transparency should exist. The gap in our understanding that could be filled but isn't.
And we can wonder if the data supported the natural hypothesis straightforwardly, would it still be hidden? Or does its concealment suggest complexity, ambiguity, or results so unexpected that release requires careful consideration? The answer waits. Europa Clipper continues toward Jupiter, carrying its secrets encoded in data files no civilian has seen. And Atlas continues outward, approaching December 19th, when Earth-based observations will either clarify or deepen the mystery. Assuming, of course, that we're allowed to see those observations when they're made. There is a branch of mathematics concerned with probability, with quantifying how likely events are to occur by chance alone. It's the mathematics of dice and cards of weather forecasting and quantum mechanics of insurance actuaries calculating risk. And it's the mathematics that, when applied to Atlas, produces a number so small, it challenges our intuition about what unlikely means.
Avi Loeb, former chair of Harvard's astronomy department and director of the Institute for Theory and Computation, compiled the anomalies systematically. Not cherry-picking observations that fit a preferred narrative, but cataloging everything about 3I Atlas that deviates from expectations for natural comets. 10 major anomalies, each with its own probability of occurring by chance. When you multiply these probabilities together, when you ask, what are the odds of all of these happening simultaneously in a single object, you get approximately 1 in 10 quadrillion, 1 in 10,000 dollars. Let's make that number tangible. The number of stars in the observable universe is estimated at around 100 billion trillion, that's 10 to the 23rd power. The number we're discussing is smaller by 7 orders of magnitude. It's rarer than finding one specific star by randomly pointing into the cosmos. But numbers this large or this small resist human intuition.
So let's walk through the calculations step by step, understanding not just the result, but what it means. Anomaly 1. Ecliptic alignment. 3I Atlas travels within 5 degrees of the ecliptic plane, the flat disk, where Earth and the other planets orbit. An object arriving randomly from interstellar space could come from any direction in 3-dimensional space. Most of that space is above or below the ecliptic plane. The probability of arriving aligned within 5 degrees by chance, approximately 0.2%, 2 in 1,000. Not impossible, but definitely noticeable. Ancient astronomers understood the ecliptic implicitly. They saw that the sun, moon, and planets all traveled along a specific band in the sky, the zodiac. They couldn't explain why, but they recognized the pattern. Modern astronomy knows it's because the solar system formed from a rotating disk of material, and that disk's orientation defines the ecliptic.
An interstellar visitor has no reason to know about our ecliptic. No reason to arrive aligned with it unless alignment serves a purpose, unless the visitor wants to maximize time spent near planetary orbits. Anomaly 2. Retrograde trajectory with multi-planet encounters. 3I Atlas doesn't just align with the ecliptic, it travels backward through it, retrograde passing near Mars, Earth, and Jupiter in a single transit. The geometry required for this is specific. Not impossible, but rare. Calculate the probability of an interstellar trajectory that brings an object within close approach distance of 3 major planets. During one pass, approximately 0.0%, 5 in 100,000. The ancient Greeks recognized that retrograde motion, when planets appear to move backward against the stars, follows patterns. Mars exhibits retrograde motion regularly as Earth overtakes it in orbit, but they struggled to explain it within their Earth-centered model.
Copernicus resolved the paradox by placing the Sun at the center and recognizing that retrograde motion is a perspective effect. For an interstellar object to arrive on a retrograde trajectory that creates optimal viewing geometry from Earth's perspective requires either extraordinary coincidence or deliberate planning. Anomaly 3. Extreme mass and velocity. 3I Atlas is roughly 1,000 times more massive than 2I Borisov, the previous interstellar comet. It's also faster traveling at speeds that suggest a powerful gravitational kick from whatever system it came from. Large, massive objects traveling at high speeds are individually rare. The probability of the third interstellar object we detect being this much larger and faster than the previous 2 Loeb estimates, less than 0.1%. This connects to von Neumann's work on self-replicating machines and optimal exploration strategies. If a civilization wants to explore the galaxy, sending large, durable craft capable of long journeys makes sense. Small objects are more likely to be destroyed by collisions with interstellar dust over billions of years. Fast objects reduce transit times. Natural objects follow the mass and velocity distributions of their parent populations. Exceptional outliers exist, but finding one in our tiny sample of 3 total detections suggests we're either extraordinarily lucky or we're not sampling randomly. Anomaly 4, fine-tuned timing. The trajectory brought 3I Atlas near Mars on October 3rd perihelion on October 29th closest to Earth on December 19th and near Jupiter on March 16th, 2026. This sequence maximizes observational opportunities within a single pass. The probability of this specific timing occurring naturally, approximately 0.005%. The same as the multi-planet encounter geometry because their related timing determines which planets you encounter.
Medieval Islamic astronomers like al-Biruni calculated planetary positions with remarkable precision, predicting conjunctions and oppositions years in advance. They understood that celestial mechanics operates on precise schedules. Events that appear to happen at the right time usually happen because the underlying physics demands that timing. For 3I Atlas, the timing seems almost choreographed. Each encounter at the moment when observation is optimal, when scientific instruments can collect maximum data, when the geometry favors detailed study. Anomaly 5. Extreme nickel emissions. Spectroscopic observations detected nickel in abundances far exceeding normal cometary compositions. Nickel appears without corresponding iron in the expected cosmic ratios. In our solar system, nickel and iron occur together, remnants of supernova nucleosynthesis that created the elements from which planets formed.
Their ratio is fairly constant, about 1 nickel atom for every 16 iron atoms. 3I Atlas shows nickel without the iron. This is chemically peculiar. Natural formation processes don't easily separate these elements, but industrial processes do. Nickel is used extensively in alloys, superalloys for high-temperature applications. Corrosion-resistant materials. The probability of natural processes producing this composition difficult to quantify precisely, but Loeb estimates it as less than 1% based on our understanding of stellar nucleosynthesis and cometary formation. Anomaly 6. The nickel-to-cyanide ratio, related but distinct. 3I Atlas exhibits a nickel-to-cyanide ratio orders of magnitude larger than any known comet. Cyanide hydrogen cyanide specifically is common in comets. It forms naturally in cold molecular clouds. Nickel is not. The extreme ratio suggests either nickel is vastly overabundant or cyanide is vastly underabundant relative to expectations. Either way, the composition is anomalous. This connects to astrobiology's search for biosignatures. We look for chemical disequilibrium compositions that thermodynamics would erase unless something actively maintains them. Life maintains chemical disequilibrium on Earth. Technology does the same. Anomaly 7. Wow signal alignment. In 1977, the Big Ear radio telescope detected a strong narrowband signal that lasted 72 seconds and was never detected again, the famous wow signal. Its origin remained unknown, though various natural explanations have been proposed. When astronomers traced 3I Atlas's trajectory backward, projecting where it came from over billions of years of galactic travel, they found it passed within about 9 degrees of the wow signal's source direction. 9 degrees is not exact alignment. It's a region of sky containing thousands of stars, but it's close enough to be interesting, especially given the uncertainties in both measurements. The probability of this alignment occurring by chance, approximately 1% based on the solid angle subtended by a 9-degree cone relative to the full sky. Ancient peoples saw comets as omens, as signs accompanying significant events. The Roman historian Josephus wrote that a comet appeared over Jerusalem before its destruction in 70 CE. Whether the association was causal or coincidental, the human instinct to connect celestial events with terrestrial significance runs deep. Maybe the wow signal and 3I Atlas are unrelated.
Maybe they're different manifestations of the same phenomenon, communication attempts from a civilization that sent both radio waves and physical probes. Anomaly 8. Rapid brightening. 3I Atlas brightened by a factor of 5 during perihelion passage. This is larger and more sudden than models predict for normal solar heating of cometary ice.
Comets do brighten as they approach the sun, but the increase should follow predictable curves based on distance and solar flux. Deviations from those curves suggest unusual activity. The probability of such rapid brightening occurring naturally in an interstellar comet, perhaps 5% based on our limited sample of observed comets exhibiting outburst behavior. Anomaly 9. Missing water signature. Early spectroscopic observations suggested a lack of water in 3I Atlas's coma. Later observations detected water, so this may be geometric or temporal observing when water production was minimal. But the initial anomaly is worth noting. Water ice is the dominant volatile in most comets. An object lacking water would require unusual formation conditions. Either very cold only CO and CO2 ice, or very hot water driven off leaving refractory material. Probability of this being a genuine compositional anomaly rather than observational artifact, perhaps 10%.
Anomaly 10. Non-gravitational acceleration without debris cloud. The most direct contradiction. The acceleration demands massive outgassing. The outgassing should create a visible debris cloud. The debris cloud is absent. This is not a small discrepancy. It's a fundamental mismatch between what physics predicts and what observations show. The probability that we simply missed detecting a 5 billion-ton debris cloud despite multiple professional observations, Loeb estimates less than 1%. The instruments are sensitive. The observations were thorough. If the cloud existed as predicted, we would see it. Now we multiply. Each anomaly has a probability of occurring naturally. The probability of all 10 occurring simultaneously is the product of individual probabilities. 0.002. Continuing through all 10. 10^16, 1 in 10 quadrillion.
This is not a rigorous statistical proof. The assumptions about independence might not hold perfectly. The individual probability estimates contain uncertainties. But even if we're off by orders of magnitude, even if the true probability is 1,000 times higher, we're still talking about events so rare they shouldn't occur in observable reality. Probabilities this small appear in physics occasionally. The probability of all the air molecules in a room spontaneously collecting in one corner, leaving you to suffocate, calculable, non-zero, but so small that it won't happen even once during the entire age of the universe. We don't plan around events with probabilities this low. We can't. If we worried about everything with non-zero probability, we'd be paralyzed. So when we encounter something with 1 in 10 quadrillion odds of occurring naturally, we have two choices: accept that we witnessed a miracle of coincidence, or reconsider our assumptions about what's natural.
In forensic science, there's a concept called beyond reasonable doubt. Not mathematical certainty that's impossible in the real world, but evidence so strong that rejecting it requires unreasonable skepticism. At what point does improbability become evidence of design? At what threshold do we transition from unlikely but possible to so unlikely that alternative explanations deserve serious consideration? The legal standard for DNA evidence accepts match probabilities around 1 in a billion as definitive. 1 in 10 quadrillion is 10 million times more extreme. Bayesian probability provides a framework for updating beliefs based on evidence. You start with a prior probability, how likely you thought something was before seeing data. Then you observe evidence and calculate how much that evidence should shift your belief.
Before detecting 3I Atlas, what was our prior probability that we'd encounter an artificial interstellar probe? Very low.
The Drake equation suggests intelligent civilizations might be rare. The Fermi paradox asks why we haven't detected them if they're common. Most scientists estimated the probability of encountering alien technology as vanishingly small, but now we have evidence. Observations that, if interpreted naturally, require accepting compounded improbabilities. Observations that, if interpreted as artificial, fit together elegantly. Bayes' theorem says we should update our prior. How much? That depends on the likelihood ratio, how much more probable the observations are under the artificial hypothesis compared to the natural hypothesis. If the natural hypothesis predicts 1 in 10 quadrillion odds, and the artificial hypothesis predicts near certainty because designed objects exhibit exactly these characteristics, then the likelihood ratio is enormous, large enough to overcome even very skeptical priors. This doesn't prove artificiality, but it makes it a hypothesis that deserves investigation rather than dismissal. When Arno Penzias and Robert Wilson detected unexpected microwave radiation in 1964, they first assumed equipment malfunction. They cleaned pigeon droppings from their antenna. They checked calibrations repeatedly. Only after exhausting mundane explanations did they accept that they'd detected the cosmic microwave background relic radiation from the Big Bang. An observation that revolutionized cosmology, won Nobel Prizes, and confirmed theoretical predictions made decades earlier. The evidence was always there, but accepting what it meant required overcoming the instinct to explain anomalies as errors rather than discoveries. We're at a similar juncture with 3I Atlas. The observations exist, the anomalies are documented. The question is whether we're willing to take seriously what the statistics are telling us. Avi Loeb receives hundreds of letters, from children asking for telescopes for Christmas, from engineers reconsidering careers, from families who never cared about astronomy now discussing whether we're alone. This matters because it reveals what's actually at stake, not just academic debates about comet composition, but fundamental questions about humanity's place in the cosmos. Charlotte Hughes from Mexico wrote that her son Marco asks about 3I Atlas news every day after school. The family that never watched the sky now follows developments together. Vladimir Kabukin's children listen to astronomy podcasts in the car instead of music. They buy books about space. One video about 3I Atlas made them go crazy about space. These aren't professional astronomers. They're people recognizing that something profound might be happening, something that could redefine what it means to be human in a potentially inhabited universe. The 1 in 10 quadrillion probability isn't just a number, it's a challenge. It asks, are you willing to follow evidence even when it leads somewhere uncomfortable? Are you brave enough to question assumptions you've held your entire life? Science advances when individuals have that courage. When Galileo looked through his telescope despite church opposition. When Darwin published despite knowing the backlash. When Einstein proposed relativity despite it contradicting Newtonian mechanics. Each faced resistance. Each challenged consensus. Each turned out to be correct. Maybe Loeb is wrong. Maybe natural explanations exist that we haven't yet discovered. Maybe the probabilities are miscalculated, the assumptions flawed, the pattern illusory. But maybe he's right. Maybe the statistics are telling us exactly what they appear to tell us, that something designed, something intentional, something intelligent has arrived in our solar system. The only way to know is to investigate thoroughly, to collect every possible data point, to test hypotheses rigorously, to let evidence determine conclusions rather than forcing conclusions onto evidence. 1 in 10 quadrillion. A number so small it barely exists. A probability so low it challenges the meaning of coincidence. The universe doesn't deal in messages. It doesn't send signs. It simply exists following physical laws indifferent to our interpretations.
But sometimes those laws produce configurations so specific, so optimized, so precisely aligned that randomness becomes the extraordinary claim rather than design. This is that moment. This is that configuration. And the number 1 in 10 quadrillion waits for us to decide what it means. There are dates that carry weight before they arrive. October 14th, 1066, the Battle of Hastings. July 20th, 1969, the moon landing. November 9th, 1989, the Berlin Wall falls. Dates when history pivots, when the world before differs fundamentally from the world after. December 19th, 2025 may become such a date, or it may pass quietly recorded in astronomical journals but unnoticed by history. The difference depends on what we observe, what we're willing to see, and whether the universe chooses this moment to reveal its secrets. On that date, 3I Atlas reaches its closest approach to Earth. Just 1.8 astronomical units, 168 million miles. Not close by terrestrial standards, but close enough that ground-based telescopes will have their optimal viewing geometry. Close enough that instruments operating at the edge of their capabilities will collect their best data. This is the moment astronomers have been preparing for since July. The moment when all the questions, all the speculation, all the careful analysis converges into observation. The moment when we either gain clarity or confront deeper mystery. On November 27th, the International Asteroid Warning Network launched a coordinated observation campaign. 2 months of intensive monitoring from November 27th through January 27th, 2026, with December 19th as the centerpiece. ION represents a global effort, dozens of observatories across continents and hemispheres contributing data pooling resources, sharing information in real time. The European Space Agency participates. NASA's assets join. Amateur astronomers with serious equipment add their observations to the collective effort. This level of coordination is rare. It typically happens for potentially hazardous asteroids objects that might impact Earth or for unique opportunities like spacecraft flybys of distant worlds. Applying it to 3I Atlas signals that the astronomical community recognizes this object's significance. The campaign focuses on astrometry precise position measurements over time. Not the sexiest science perhaps, but foundational. Knowing exactly where 3I Atlas is at any moment and how that position changes allows astronomers to refine trajectory predictions, detect additional non-gravitational accelerations, and determine whether forces acting on the object remain constant or evolve as it moves through different regions of space. If 3I Atlas is natural, a typical comet despite its interstellar origin, then its behavior should become more predictable as observations accumulate. Activity should correlate with solar distance. As the comet recedes from the sun, outgassing should decrease, brightness should fade, trajectory should stabilize. The astrometry campaign will test these predictions. If data confirms them, the natural hypothesis gains support. If data shows continued anomalies, unexpected accelerations, behaviors uncorrelated with solar distance trajectory, changes that shouldn't occur, then natural explanations weaken. Avi Loeb directs the Galileo Project, a scientific initiative dedicated to detecting and characterizing anomalous aerial phenomena and potential extraterrestrial technological objects. Funded privately, operating independently from government agencies, it represents a serious attempt to investigate questions that mainstream science often avoids. Loeb alerted the project's research team in October, watch for unusual activity near Earth during the coming months. Not just 3I Atlas directly, but the space around it, secondary objects, trajectory adjustments, anything suggesting the interstellar visitor might deploy equipment or perform maneuvers as it approaches our planet. The Galileo Project operates multiple observatories equipped with instruments designed specifically for this purpose. Wide-field cameras to survey large regions of sky, infrared detectors to spot thermal signatures, radio receivers to detect potential transmissions. All coordinated, all recording, all searching for signals that don't fit natural patterns. This represents a different philosophical approach from traditional astronomy. Instead of assuming everything is natural until proven otherwise, the Galileo project explicitly searches for artificial signatures while remaining rigorously scientific in methodology. Critics argue this biases investigation toward false positives, seeing artificiality where none exists. Supporters counter that mainstream astronomy biases toward false negatives, missing genuine artificial signals because no one looks for them seriously. Both perspectives have merit. The question is which error we're more comfortable making, mistakenly claiming something is artificial or mistakenly dismissing something artificial as natural. December 19th observations will target several specific objectives. Spectroscopy. Detailed analysis of light from 3I Atlas's Comet split into component wavelengths.
This reveals composition, which molecules are present in what abundances in what ionization states. If 3I Atlas is natural, its spectrum should resemble other comets. Water, carbon dioxide, carbon monoxide, ammonia, methane. The usual volatiles that sublimate as ice heats. If the nickel anomaly is real, spectroscopy should confirm it. If industrial materials are present, they'll show characteristic emission or absorption lines. If the composition is truly anomalous, detailed spectroscopy will make that undeniable. High-resolution imaging. Using adaptive optics to compensate for atmospheric turbulence, large telescopes can achieve resolution approaching theoretical limits. For bright objects at 1.8 AU, this means detecting features the size of small cities on 3I Atlas's surface. Natural comets show irregular shapes, potato-like, the result of accretion and occasional collisions. Artificial objects might show geometric regularity, right angles, symmetries.
Surface patterns that geology doesn't produce. Even detecting rotation period and axis helps. Tumbling chaotically suggests natural rubble pile. Controlled rotation suggests internal structure, possible spin, stabilization, maybe even active attitude control. Polarimetry. The polarization of reflected sunlight depends on surface properties, texture, composition, particle size distribution. Cometary dust produces characteristic polarization that we understand from decades of observation. Metallic surfaces polarize light differently. Smooth geometric structures produce different signatures than rough, irregular terrain. If 3I Atlas has artificial components, polarimetry might reveal them even if imaging resolution remains insufficient to see structure directly. Photometric monitoring. Continuous brightness measurements over hours and days reveal rotation periods, outburst events, and activity changes. Natural comets follow predictable brightness curves based on solar distance.
Deviations suggest something unusual. If 3I Atlas brightens or dims in ways uncorrelated with solar distance, if patterns appear that suggest intentional signaling, if periodicities emerge that don't match natural rotation, these would be significant findings. Search for secondary objects. Is 3I Atlas alone, or does it have companions? Wide-field surveys around the primary object can detect smaller bodies traveling nearby, either natural fragments or potentially deployed probes. V1 Borisov already occupies one such position. Are there others? Survey campaigns will search systematically, looking for anything moving with 3I Atlas or in orbits that suggest association. Radio monitoring. The Galileo project and other initiatives will monitor radio frequencies for potential transmissions, not expecting messages in English, obviously, but looking for narrowband signals, repeating patterns, modulations that don't match natural radio sources. This is SETI applied specifically to 3I Atlas. If the object is technological, if it communicates, if signals are being transmitted back toward wherever it came from, December 19th's close approach might be when we're best positioned to intercept those signals. Loeb emphasized that any telescope with aperture larger than 30 centimeters, about 12 inches, can observe 3I Atlas on December 19th. That's accessible to serious amateur astronomers. Thousands of people worldwide own such equipment. This democratization matters. Professional observatories operate on fixed schedules with limited time. Amateur observers provide flexibility watching when professionals can't, covering regions of sky that large surveys miss, contributing data points that fill gaps in professional coverage. The discovery of 3I Atlas itself came from Atlas, a survey telescope that operates somewhere between professional and amateur scales. Gennady Borisov found V1 Borisov with a custom-built half-meter telescope. These aren't multi-billion-dollar facilities, they're dedicated instruments operated by passionate individuals. If something unusual happens on December 19th, a sudden brightness change, an unexpected trajectory adjustment, a visible secondary object, amateurs might be first to notice. They watch with different priorities than professionals less constrained by observation proposals and peer review pressure. This bears repeating. 3I Atlas will not return. Its orbit is hyperbolic. After passing Earth and continuing to Jupiter, it exits the solar system forever. Whatever observations we fail to make during this encounter cannot be repeated. This creates urgency, mistakes, equipment failures, bad weather. Any factor preventing optimal observation on December 19th represents permanent lost opportunity. Ancient astronomers understood this about rare celestial events. Solar eclipses occur on specific dates, at specific locations, visible briefly before the moon moves on. Miss the opportunity, and you wait years or decades for the next one, or travel thousands of miles to reach the path of totality. For 3I Atlas, there is no next time. This is it. The convergence happens once. Ideally, December 19th produces data so clear, so comprehensive, so definitive that remaining questions resolve. Either we confirm natural cometary behavior beyond reasonable doubt, or we detect signatures so anomalous that artificiality becomes the simpler explanation. More likely, we gain incremental clarity. Some questions answered, others raised. The pattern of anomalies either strengthens or weakens based on what new observations show. But even incomplete answers advance understanding. Even ambiguous results narrow possibilities. The goal isn't perfection, it's progress toward truth, wherever that truth leads.
There's something profound about a global community, turning instruments skyward, simultaneously focusing collective attention on a single object moving through the dark. It echoes ancient practices, solstice gatherings, eclipse observations, comet watches that brought communities together in shared wonder. We've gained technology since then. Our instruments see wavelengths ancient peoples couldn't imagine. Our mathematics predicts with precision, their philosophy only approximated. But the fundamental act remains unchanged, humans looking up, asking what that light means, seeking understanding of our place in the cosmos. December 19th represents that act at its most coordinated and consequential. Whatever we find or fail to find shapes how we understand ourselves and our cosmic context. The convergence approaches, the date waits, and somewhere between Earth and Jupiter, 3I Atlas continues its journey, carrying answers to questions we're only now learning to ask properly.
We have walked through the evidence together. From discovery to data observation to interpretation, science to speculation, we have examined 10 anomalies, traced 2 trajectories, confronted uncomfortable questions about what moves through our solar system and whether we're ready to understand it. Let us gather the threads. V1 Borisov appeared on November 2nd, discovered by the same astronomer who found 2I Borisov. It sits between 3I Atlas and Earth, positioned with geometric precision that probability alone struggles to explain. It lacks the tail comets should display at its solar distance. It arrived days after 3I Atlas completed perihelion, exactly when optimal deployment mechanics would predict. 3i Atlas itself exhibits behavior that doesn't fit comfortable models. Retrograde orbit aligned with the ecliptic plane, a configuration occurring naturally in only 2 per 1,000 interstellar arrivals. Trajectory bringing it near Mars, Earth, and Jupiter in a single pass, a sequence occurring naturally in only 5 per 100,000 cases. Sunward jet defying normal tail physics, non-gravitational acceleration requiring catastrophic mass loss that produces no visible debris cloud, blue coloration suggesting intense energy processes, rapid brightening inconsistent with gradual solar heating. NASA's Mars Reconnaissance Orbiter captured unprecedented images. They remain unreleased. Europa Clipper sampled the ion tail in situ. The data remains withheld. ESA photographed the object 488 times and released 2 images. China shared openly what Western agencies guard. Avi Loeb calculated the compounding probability of all anomalies occurring naturally by chance, less than 1 in 10 quadrillion, a number so small that invoking coincidence requires more faith than accepting design. And still definitive proof eludes us. We have patterns, not certainty.
Inference, not evidence so overwhelming that denial becomes impossible. This is where we stand. Not at answers, but at questions. Not at conclusions, but at a threshold where what we choose to investigate determines what we're capable of understanding. 3i Atlas is an interstellar visitor, hyperbolic orbit origin beyond our solar system, traveling for potentially billions of years before arriving here. This alone is remarkable, only the 3rd such object ever detected. V1 Borisov is real. 10 observatories confirmed it. Its position between 3i Atlas and Earth is measurable, geometric, undeniable. Non-gravitational acceleration is confirmed. NASA published the measurements, 3.7 standard deviations above noise. The comet is moving in ways gravity alone cannot explain. The expected massive debris cloud is absent. Multiple observations over weeks show compact nucleus without the extensive coma and tail that 5 billion tons of expelled material should create. These are facts, not interpretations, not models, not theories. Observations that any qualified astronomer can verify. Whether these objects are natural or artificial, whether 3i Atlas is a comet with unusual properties or technology with camouflage, we're only beginning to penetrate. Whether V1 Borisov is a separately random arrival or a deployed probe, what the withheld data shows. Whether high-rise images reveal surface features that explain everything naturally or display structures that challenge our entire framework. Whether Europa Clipper detected normal cometary composition or something we've never encountered. What will happen on December 19th? Whether observations will resolve ambiguities or deepen mysteries. Whether we'll gain clarity or confront even more perplexing evidence. How this story ends. Whether 3i Atlas and its potential companions will depart quietly, leaving us with fascinating scientific puzzles but no paradigm shift. Or whether something will occur, a signal, a maneuver, an undeniable signature that forces us to acknowledge we are not alone. On a clear night, if you look toward the region of sky where 3i Atlas travels, you might wonder, is something there looking back? Not with eyes like ours, perhaps. Not with consciousness we'd recognize as similar to human awareness, but observing nonetheless. Recording, learning, reporting back. Across distances that dwarf our comprehension to intelligence we cannot fathom for purposes we cannot guess. Or perhaps there's nothing there but ice and rock and the beautiful indifferent machinery of gravity and momentum. Perhaps the universe really is as empty as our loneliness sometimes suggests. Perhaps every anomaly has natural explanations we haven't yet discovered. And the pattern we think we see is just pareidolia, finding faces in clouds, meaning in randomness. We'll know soon. December 19th approaches. The International Asteroid Warning Network coordinates observations. The Galileo Project prepares its instruments.
Amateur astronomers around the world point their telescopes skyward, participating in discovery as Gennady Borisov did when he found V1 Borisov through patience, dedication, and the willingness to look. The data will accumulate. Spectroscopy will reveal composition. Photometry will chart brightness variations. Astrometry will track position with precision. And somewhere in those measurements, in the patterns they form or the patterns they break, we'll find answers. Or we'll find deeper questions. Either outcome advances understanding. Either conclusion is preferable to the certainty that comes from not looking at all. The question, are we alone, is as old as consciousness. Every culture that watched the sky wondered. Babylonians, Egyptians, Mayans, Greeks, all asked whether the lights above represented places, worlds, homes for other minds. For most of history, we could only speculate. The tools didn't exist to investigate empirically. Philosophy and mythology filled the void where data should have been. Now we have tools. Telescopes that see across the electromagnetic spectrum. Spacecraft that can touch what we once only imagined. Mathematics that predicts models, tests hypotheses against observation. And we have 3i Atlas, an opportunity to apply our tools to a question that matters more than any academic exercise, any distant curiosity. If we're being visited, if intelligence from beyond our world has arrived to study us, then everything changes. Our place in the cosmos, our sense of isolation, our assumptions about uniqueness and specialness and cosmic significance, all of it gets rewritten. If we're not being visited, if these are natural objects, however unusual, then the universe remains as we thought. Vast, mostly empty. With intelligence, a rare accident of chemistry that perhaps happens elsewhere but hasn't yet reached here. Either way, we need to know. Not assume, not prefer one answer because it's more comfortable or less disturbing. Know based on evidence strong enough to support conclusions that withstand scrutiny. That requires honest investigation, transparent data, willingness to follow evidence even when it leads somewhere we didn't expect. We are the generation that must answer this, not our descendants. Not future civilizations with better technology and clearer perspective. Us. 3i Atlas will not return. Its orbit is hyperbolic. It came from the interstellar dark, passes through once and returns to that dark. Whatever understanding we gain comes from observations made now during this brief window when it transits our neighborhood. If we fail to investigate thoroughly, if we allow bureaucracy or fear or institutional inertia to prevent collecting the data needed for conclusions, then we fail not just ourselves, but every generation that comes after. They'll look back and wonder, how could you have had this opportunity and wasted it? How could you have seen something unprecedented and chosen comfort over curiosity? We have the tools, we have the opportunity. What we need is courage, the courage to look clearly, to report honestly, to accept what we find, even if it unsettles everything we thought we knew. And so we stand here at the end of this journey through data and inference at the beginning of something we cannot yet name. V1 Borisov sits between us and 3i Atlas, two objects from beyond aligned in space in ways that suggest purpose or represent staggering coincidence. They move according to laws we can measure, carrying implications we're only beginning to process. December 19th waits, a date on the calendar. A point in orbital geometry, a moment when convergence brings the interstellar visitor to its closest approach and our instruments to their optimal vantage. What we'll see, we don't yet know, but we will look. We must look, because looking, observing, measuring, testing, questioning is what separates knowledge from ignorance, understanding from fear. The universe has shown us something, not with fanfare, not with unmistakable signals that remove all doubt, but quietly, subtly, in the language of orbital mechanics and spectroscopy and geometric alignment. Whether that something is profound or mundane, revolutionary or routine, we owe it to ourselves to find out. The sky changed on November 2nd when V1 Borisov was discovered. It had already changed on July 1st when 3I Atlas appeared. And it will change again, has already changed in ways we're only beginning to recognize. We live in the era when interstellar visitors arrive not as myths, but as measurable objects, when the question of cosmic companionship transitions from philosophy to physics, when what we thought was impossible becomes merely unexplained. This is privilege and burden both. Privilege to witness what no previous generation could. Burden to investigate responsibly, to think clearly, to resist both credulity and closed-mindedness. The universe waits patiently. It doesn't hurry. It doesn't care whether we understand. It simply continues following laws we've partially decoded, harboring complexities we've barely begun to comprehend. And somewhere in that vastness, 3I Atlas travels, with or without companions, natural or designed, alone or part of something larger. We watch, we measure, we wonder. And in that wondering, in that persistent questioning that defines our species at its best, we participate in something ancient and essential, the human need to understand our place in the cosmos, to know whether the lights above are merely physics or something more. The answer arrives soon, not in speculation but in data, not in preference but in what the observations actually show. Until then, look up. The sky holds mysteries yet, and some of those mysteries might be looking back. Welcome to the threshold. Welcome to the question that defines our moment. Are we alone? The universe is about to reply.